Alright, hello, welcome back. I did some stuff between last time and this. I did some of these smaller stuff. I implemented the rest of the arithmetic stuff, and I forgot to add this here. I think the where is it? I've got to add it here. Logical operators as well, and then we need the compare stuff. So I added the rest of the arithmetic. So all of this now works with floats as well. And what I did was also I found out a nice way of kind of making, well, how should I say, like a comp time arithmetic and comp time Boolean algebra. So basically I made this evaluate arithmetic function. I mean, it's very simple, really. It's just, it takes two values. Now, these values could be either resolved values, so that we actually get the actual value out. Like, they can be runtime values. It can also be comp time values. So it doesn't really matter. It can be anything. And if it's like, if like any of these are locations, that means that we can't evaluate it right now. So actually, we could also, I mean, you could look at it like this. If this is an address, or if this is an address, then we have to return null, because we can't evaluate it at this time. But if it's like a integer or a float, we can actually, you know, evaluate it here, and that means that now we're using that in compile binary for add, subtract, multiply, divide, remainder. So all of these operators, first we compile these expressions, and then we evaluate the arithmetic, and if we get a value back, that means that both of these values were actually hard-coded, or they were, you know, they were constants, or yeah, literals basically. And so we evaluate the arithmetic. If we get a comp time result, we can just return the comp time result. So we don't end up with any instructions here, except for these, I guess these. Well, if these were comp time known, then this wouldn't end up in as instructions either. So yeah, so it kind of works out by itself there. But if we didn't get a comp time result, we continue here and we create a ref and we add an instruction to have the runtime evaluate what the result will be. Okay, and then I also added, also this is reused now, so it's reused in both the comp time here, but also in the in this is the runtime. So here we resolve both values, and they could be, you know, an address that we actually go into the virtual machine and check what is the value, you know, and then we can evaluate arithmetic on those values, because now we know that there has to be some value that, or there has to be some result that we get out there. Actually, you know what? If we get a null out here, this would actually be an error here. So there we go. All right, and then I did the same for the logical. So, and this was even more simple actually, but it's a little bit different, because the logicals, like, you know, and or Boolean expressions or logical expressions, they can short circuit. So that means that if, for example, if you have like left and right, this is like pretty common in programming language. If you have like something that is, let's say, something that is truth or true, I mean, and false, what's happening here is that for the AND operator, if the first thing is true, basically the whole result of this expression is going to be equal to the right hand side, like this false here. But that could be, doesn't have to be false, it can be anything basically. So and then if you have like false or true, let's say, this is the other way around. So this, if in an OR expression, if this is false, if the left hand side is false, so we only check the left hand side. If the left hand side is false, then we return the right hand side. So really, I'm gonna call this the right hand side, and then no, this, yeah, this is the same thing, but it's the other way around, where this is true and this is false, right? But then if you have like false and right, now this will become the left hand side because we don't need to worry about right now, so we don't even need to evaluate it. And in the case of the comp time, actually we don't even compile the right hand side. Like if the left hand side is actually determined, could be determined in compile time, we don't even need to compile the right time, that the right hand side, that doesn't even need to be an expression in the final, in the instructions. So we can just return this the left hand side directly. However, for a, let's say for an OR that is true on the left hand side, well, this is the same thing here. So this is also now the left hand side because this is true, so we don't need to check the right hand side. So this doesn't even compile if we can get this in runtime, or I mean in compile time. So and then, if you have, so that's the short circuit. So in comp time here, we try to evaluate only that, we're only looking at the left value. So we're only compiling the left value. We're checking first, okay, is it comp time known? Then we can actually just then we can evaluate this expression directly. And how I did it here is basically the result that we get out is a left or right enum. So if we get a left, that means that we should the whole result of the logical is going to be the left hand side. If it's right, it's going to be the right hand side. So that way we don't have to supply the right value here. We can return this kind of event or result thing, and then whatever is using this function could decide on what to do with that information. So and here we just simply have this logic here where we have we're looking at the operator. If we have AND, we check if left is a boolean, or exit code is same thing, and if it's a success, that means it's true. We return the right hand side because AND, that's how AND works. Otherwise we return the left hand side, so either we return right or left. And for the OR, yo, welcome. If the left hand side is a boolean and it's success, we return the left hand side, otherwise the right hand side. So now we know that otherwise it's a null. So that means that, well, if the left hand side is a boolean, that means it's a comp time non-boolean, unless you run this from a runtime standpoint, in which case it's runtime known. But right, so when we run this, we would only supply the left hand value and we get the comp time result out. If we get left, we just return the left expression. We don't even need to compile the right hand side. If we have the right hand side, that means we need to compile the right hand side, but we just return the right hand side. We don't even need to kind of do anything with the left hand side. We just return the right hand side, and the left hand side will kind of disappear in it won't end up anywhere. we just use the right hand side. So that's how you can kind of the short circuit with the comp time will not even include things in the instructions. But if we don't have a comp time result, we continue down here and we compile the right hand side, we create a ref to store the result, and we add this instruction to be run later in the runtime evaluator. So now if we look at the runtime, it's also using the same function. So we don't need to repeat that logic, which is really nice. Now this one does have to resolve these values, even though maybe the right hand side is not needed. Although we could wait with this until we're over here actually. So we don't actually need to do that. We could do like resolve value. Yeah, we don't really need the right. Actually, this is not even used. Yeah, okay. It was used here before, so now I remove that. Move that over there. Wait, resolve value. Yeah. So same thing basically, but a little bit different. So we resolve the value of the left-hand side. That could be from comp time, or actually it's never comp time. It's always going to be runtime norm. So it's from some sort of location where we get where this is stored, and then we evaluate, you know, the logical depending on the operator and the left value. So we're reusing the same function here, and we're looking at the result. And if the result is left, then we use the left hand side. If it's right, then we use the right hand side. So yeah, pretty simple there. Also here we should also consider returning binary unsupported expression as well, because getting null means that we didn't match like the Boolean values. And also this kind of technically means that also the right hand side doesn't have to be a Boolean value. It can actually be anything right now. But I think the type checker will complain probably. We'll see what happens with that. Hello ByteWard05, what are we making? We are making a bash-like scripting language. I can show you here. So here you have, like, on the left hand side you have the language that I'm making here, Runic is called, and on the right hand side is bash. So you can kind of see the comparisons. So this is like, yeah, this is bash, this is my language. So you can see that the differences are the pipelines kind of look the same, but then there's differences in the if statements. And so you can see here this has, like, you know, a C-like syntax, or actually a zig-like syntax, and this is of course bash here. And then you know, we have for loops. So it's basically just making a bash, making this language except like this. Simply put. All right, yeah. So so now the logicals should work as well. So I think I had a test for that. So here are a bunch of these expressions, and you can see the results out here. Now notice that true and true equals 0. That means 0, because 0 means success. So it's actually, this is actually the true value, and 1 means, well, non-zero really means false. So this is false. Everywhere you see 1 is false. So it's kind of backward from the C. If you compare to C, for example, where 1 is true and 0 is false. But yeah, this is how it works. IR stands for intermediate representation, I think. It's basically So .rn, that's runic. That's the language that I'm making. And then IR is basically just I already built a lot of stuff in before, but now I'm kind of remaking because man, what's it called? I'm failing to find words. Basically, we had trouble with implementing streaming pipes with blocks. So if I show you here, if you have a block of code and then you pipe that into something else, we had problems actually implementing this before because of technical reasons. So I decided to make an IR, which is basically kind of like a language that sits, well, normally it sits between the language, the program language, and kind of assembly code. Except we're not actually compiling to assembly code in this language, but we are compiling to kind of like an IR language. So I can show you that as well. Like if we take this, for example, maybe this is a long example here, but let's just take like IR. I think I have like basic here, and then we compile this. And here you can see this is the result of the IR. Basically, you get a little kind of like a program here. So we have read-only data, and then we have some other information here. We have, but then you get like instructions. So this is the language that is the IR language. So it's basically, instead of being, yeah, as you can see here, this is kind of like a list of instructions. So it's closer to assembly code in that sense, because it's just a list of instructions instead of usually a language like this is like a tree structure, tree-like structure. But this language is more like a list structure. And then it becomes easier to kind of just step through, because you have a list of instructions that you step through one at a time. And that in turn enables us to have things like virtual threads. And why do we need virtual threads? Well, we need virtual threads in order to stream data from one process to another process. Or at least that's my solution here. But yeah, and also you could enable other things like asynchronous execution and all that as well. But yeah, this is the IR. So this is kind of compiled into this down here, you can say. And then this also gets executed by an interpreter, or like in a virtual machine. So that's how we run the program later. So if I press my button here, you can see this is the result, this is the output of the program, and then this is like the compilation result. And then you can also go down here to see, here's like the execution part. So here's where we start to run and you can see every step being executed here. Yeah. And then we exit at the end. So that's what IR means, basically, in this context here. And I'm currently reworking like the whole language in this version so that we can get more support for streaming pipes and stuff. All right, so now the thing that we are missing from, well, I would like to add this compare, because I have like a pattern for this now. So we have implemented arithmetic and logical operators for binary operators, and I'm just going to add compare so you can follow along to see how that's done now. So basically we have this compare operator, which is like greater than, equal, less than, equal, or not equal. And that is a binary operation with this compare instruction. So this is how the compare instruction works. So basically what we need to do is we need to go to well, first of all, I want to add compare to the format here so we can format it nicely. And I want to go to the compiler. Actually, I want to go to the evaluator first in this case, because we have this evaluate logical, evaluate arithmetic, and evaluate compare is going to be very similar to probably evaluate arithmetic. I'm going to copy this and put it over here. So we're going to have evaluate compare, and this is a compare operator. And we have two values, and then we get some kind of value back, which is going to be a Boolean value. But we'll see. Actually, let's just remove all this. So this is going to be like greater than, for example. Let's just do one example and we can see what we need to do here. So first we need to check, can we even compare these two values? Like what kind of values can we compare? One second here. All right. So let's just check if the left-hand side is, for example, a U integer, and the right-hand side is a U integer. Now, of course, we could compare those, except we could also compare technically, like if this was a U integer and this is a float, for example, we could compare those also. So if the left-hand side is an integer, I guess what we could do is like is left number. Maybe we can even add, we could add like a convenience function here for that. So is number so we're either a U integer or we are a float. Okay. So now we can say if left hand side is a number and the right hand side is a number. Now you could also do because now we want to get the actual value out as well. I'm not sure if there's a good way of checking that. Because I was thinking like is number, this could either be a bool, and then you can easily convert a bool to an optional, but then it's like what would this type be? Like, because it could be, I mean we could do a union, and we could do a new tagged union which is like a number. We could also change so that we only deal with floats, but I don't know. We could do it like a new union enum called a number. I'm just gonna do this for convenience right now. So this is either a U integer, which I think is like an I64. No, oh yeah, it's a U size, that's right. And then a float, which is an F64. And then, so this would be a, maybe a number. And so if, actually let's do switch on self. If we're a U integer, we return, let's do return over here. We return a U integer. Or if we're a float. Otherwise, we get null. Right. Oh yeah. Sorry, this is not correct syntax. Sorry. Okay. Now we're kind of moving the goalpost here, but we could add a function here, I guess. No, this is stupid. Yeah, we're just moving the goalposts. I think the problem that I wanted to avoid is basically, I want to basically say left is just end up with this somehow. But I mean, what you could do is maybe you can have a greater than function, let's say, where you take like left is any type, right is any type, and then this would be a bool. I mean, this would be equivalent of just saying left like this directly. Yeah, so this is like stupid. It's like the problem is, if we could return a sum type here, that would kind of solve the issue. But I don't think we can. Unless we turn this into like a comp time node. No, I think we're just moving the goalpost. But this could be good. This could be good to have as well. I'm gonna remove this, and this is gonna be true, true, and false. Okay, let's just do this, because what we can do is we can say, okay, well, if left-hand side is a number and right-hand side is a number, but now we still need to check what they are. God damn it. Okay, you know what? Maybe it's easier if we do like, we just have to hard code in this. Well, if left hand side is integer, we do return that doesn't make sense. And then we switch on right. We see, okay, well, if you're a U integer or if we get that, and we'll return if left U integer is less than R, then we return, well, actually we can just return exit code. Yeah, we have from boolean, so we can just do from boolean. There we go. So that will create that. Then if we have float, we have to do the same thing. Except here you could use inline float, so you don't have to repeat the argument. Now this would become like a... but then when we compare, how does that work with zig? Does that even work? And then if this is anything else, we have to return null. Yeah. I mean, I guess we could do switch on left. Do the same thing here, like inline new integer float. And that's the left hand side. Yeah. Then u would be left. I mean, it says u type, but it could be, or u size, I mean, but it could be like this or this, I think. But I'm not sure how Zig does with like comparing u size with floats. But I guess we'll find out. Because we're not calling this function, so I think some of the checks are not done here. But yeah, okay. So we only need to have the operation in one place, so that's pretty good. We could also say like return from here, so we don't have to do all this actually. And then we don't need that. There we go. Okay. Now, let's go to compiler and we will import this function. Compare. And now we need to handle these binary things. So this would be like greater equal less equal not equal. Is that it? I think so. So all those operators, and I'm gonna copy this. So we have the left and right hand side, both need to be compiled, so that's fine. And then we can evaluate compare instead. And then if we get a comp time result, we can return that. Otherwise, we will have a compare result, and we have a compare instruction. Yeah, that's basically it here. And then we need to also do the evaluator here. But now we should get more errors here. Okay. So that's greater than. I guess we can just do like greater than equal. Oh, does this look like greater than? Less than. It's just that I wish we could like generalize this even more, but okay, and then equal and not equal. All right. However, equal and not equal, of course, could work with other things for like numbers. It could work with strings, for example. So if we have a string, I think a string is just a slice actually. I forgot. Yeah, it's a slice. I mean, we also have address, but that's kind of weird. We have exit codes. We could check exit code equals as well. So if we have a slice, and now comes also the question like, okay, well, what if you compare a string to a number? That shouldn't, that should be like type checked. You have to kind of convert first, I would think. We'll see what happens. I mean, it's supposed to be an easy to use scripting language as well, so. Now this is a slice, we get an R. But these slices, actually slices are, we can't use slices here because they are address. Yeah. Unless it's like a read-only address, then we can actually use it, but okay. How would we deal with that? Okay, I'm gonna put this in on hold for now. But what we could do is we could do exit code. However, that doesn't really work. Oh, well, let's forget about this for now. I'll only do the numbers for now. Let's just get this in here. What else is there? There's nothing else. Oh, I see. It's this else here. It's complaining about. And now probably we get a whole bunch of errors. Yeah, expected type F64 found user. So we can't actually do this comparison. Damn it. But we could try to, like, if one of them is a float, we could convert the other thing to a float and then compare. So if we're a new integer, we return a float from int. And if we're a float, we return the float. Otherwise, no. Okay, now we can turn it into a float. So I mean, basically we could just turn everything to floats. Okay, but then this changes this a little bit. So we'll do like if left to float, and then if right to float, we return left greater than right. So now these should be floats, yeah. Otherwise, we don't have anything that can be turned into something that we can compare, so we have to return null. So there we go. So we'll have to do that. Well, this is good anyways, because we had other weird things to do anyway. Oh. Okay. Expected found bool. Oh yeah, from bool, yeah, that's right. Okay. Now this is compiling. So let's go to evaluate here. Okay. I'm gonna copy this, put this over here. And then now we have the compare function, or the compare instruction, which is basically going to be the exact same pattern here. So these three are actually, they're kind of like exactly the same pattern, so I'm almost contemplating on generalizing that as well. But yeah, it's kind of simple anyway, so it's not really... Oh, all cases handled, okay. I'm just gonna do that then. Cool, so all instructions are now handled. That's good. Although we probably maybe need more, I'm not sure actually, but... Okay, so... Okay, yeah, let's try it out now. So let's make compare. Now I still have to like echo these out, but I guess we're gonna compare like, is 1 less than 2, for example, and that is true. I mean, 0 means true, so that's good. Is 1 more than true? Greater than true? Sorry. Yes or no? I mean. It's a little bit confusing with the ones and zeros as true and false, but what else do we have? Like 1 more equal, so 5, 4. Let's just try mixing these as well a little bit. That should be 0, yes, but then we increase you to be 5.5. Still be 0, and then 5.6 should be 1. All right, and let's just 10 more than or equal to 10. And I guess 11. yeah. And then we have 3 is equal to 3. Very good. 3.5 is equal to 3.5. Yes. 3 is equal to 3.5. No. Great. And then let's just change all the equals to not equals. And there we go. That's the other way around. Cool. Actually, you could do like a cool thing. You could, let's make this into a block. And then I'm gonna do like column. I forgot how to do this. I have to check the MVP here. So let's do column T S, and the separator I'm gonna do like this, perhaps. No. Okay, there we go. So a little bit more like nicely formatted. It's a nice thing that you can use these tools. I know, like, just, you know, I basically know nothing about kind of the terminal tools. But it's nice when you find this, because there's so much already out there that you can use. So this is kind of cool. It's nice to have that working, and since we can make blocks and pipe them into other stuff, we can easily do all this. Awesome. And then also don't have formatting, but what is it? Compare logical arithmetic, that's right. Awesome. Okay, cool. So that was compare. Excuse me. Oh man. Excuse me. All right. So, what do we want to do next? So maybe one of the larger ones. We have, you know, we do have a bunch of stuff that we need to kind of fix in order for this language to be kind of complete, I guess you could say. I mean, we could always add more stuff and stuff, but what I want for like the kind of the MVP of the language is well, it's a couple more things that are actually not in here yet, but I mean, these things are gonna be crucial, of course. All the bash, like pipeline stuff. The like you can define functions and call them, but we don't handle arguments. So that might be maybe one of the things we need to do. I mean, of course, that's going to be part of MVP, of course. We have fixed ref bugs now. Yeah, so we have kind of like a crisis right now with the how we store, like how you could say we don't really have heap allocated things. But we could, that's also something that we need to add, like garbage collection and how to kind of work with these. I guess the refs right now are a way to kind of allocate stuff on the heap. However, they are like globals, and when you create a function, let's say when you declare a function, we create a ref, and then that ref has an address, so it's like a global address and it's comp time known. So it's like if you use that ref like multiple times, if you call the function multiple times, the refs are gonna collide. And so we need a more dynamic way of creating space to keep stuff in it. And that could drastically change some parts of the compiler. But that is one of the huge things that we need to actually fix in order to, because now you can't actually call a function multiple times. Like even if you have a very basic function, so this is a function here, and it echoes a bunch of stuff, and then we pipe that into grep. So that all works. However, let's say we want to do it again. Now we get an error because we get duplicate ref, because the instructions, the IR instructions that are in here are like ran again. And we don't actually have kind of like support for that. So we need to have support for having kind of instructions that creates these refs, have, you know, support for being able to be ran multiple times. So yeah, I mean, also that would be a problem when having a something like a for loop as well. That would be also be something to fix. But maybe that's what I should focus on, since that's on my mind right now, like the ref stuff. So basically we have a ref instruction. The thing about the ref instruction is that it includes the actual address that we're storing it in, which would not be the... It's kind of like a comp time known address. So yeah, it doesn't really work. So what would we need to do? So we, I mean, we need to kind of so what's happening is that while during compilation we are actually generating these addresses, and we can't do that. We have to kind of in the runtime generate the address of the ref instead, and that means that the virtual machine will have to kind of provide new addresses for values. So we need to build that that whole thing. So here is the evaluator. So this is including all of the like virtual machine, and in this context here, so this is the program context. This has everything, you know, the threads, the memory, everything that like the instruction counter. It's kind of like like a virtual machine. And then we have a config and an allocator as well. But this evaluator will like change the context. It would like step through the instructions, and it would evaluate the instructions and then change the program context accordingly. And so if we look here, we have a bunch of stuff. We have shared, we have so shared is basically like read-only data. The instructions are not gonna change. Basically things that's basically not gonna change. And of course we have the refs that are shared. It's also like shared between threads. However, now the refs will be a bit different. I'm just trying to figure out how in the instructions we would solve this. Are you teaching or making? I mean, I'm doing kind of both, I guess. I think a lot of my audience is interested in development, so I like to talk about, you know, how to do stuff as well and how it's implemented and discuss, you know, different programming things. And also, like right now, I'm teaching. I'm teaching myself how to do this, because this is like, I've never done this before. So it's like we're going through it. I'm going through my thought processes as I make it as well. So IO runtime refs. So what I'm thinking here is like, let's say, well, for example, let's say you have a binding, so some kind of binding, you know. Okay. Now what should happen here? Well, some things are happening. So basically we're declaring S in this scope. That is one thing that is happening. But it's also like in the instructions, we don't really see that, I don't think. It's only during compilation that we actually see that. When we run the instructions, we don't know anything about the identifier S. We kind of talk about S as a location where data is held. Or it could be, I mean, it could also be like comp time known in extension, but this probably will become like, because hello is gonna be stored in read only, which means that S will actually point to that place in the read only data. So S will be declared. So this will be declare S as read only, you know, address 0 or whatever, wherever this is stored. So that is declared as that. So whenever we use S in the compilation, so for example we echo S, that will now point to, that will be this location, whatever this is, like that, it will point to this read-only data. So so that will be that. But for example, okay, another easy example is just echo hello. Well, it's kind of a lot going on. It's like, yeah, it looks like an easy example, but there's a lot going on here in the background. We're spinning up this process, you know, we're calling echo as an executable, we're forking, we're actually creating we're creating one fork, and then we're also waiting for that thread to end, and we're also streaming data as well. So there's a lot going on with just calling this executable here. So as you can see, like if we compile this, for example, oh, what's happening here? Okay, I'm not sure what happened there. If we compile this, we get all this stuff in the like 41 bytes. It's not that much, you know, but in the read-only data we get this, and then we also get like instructions here. So we get these are the instructions that are like for this specific program, and then this is like common on all programs. Like this is kind of like the setup of all programs. And then these sets down here, instruction sets, are also part of the program. So basically what's happening is this is where the program starts, you could say, the real program. And here we're already creating a ref, right? A ref for the thread that gets executed. So basically what we're doing is we're creating a variable location that we can store this fork then the thread handle that this fork will produce. So that is stored in this ref. And then we wait, and we wait for the same ref here. So we're waiting for that. So basically we're creating a variable. We're storing the result of this fork in the variable, which is just a thread handle. And then we're waiting for that thread handle to complete. So that's all what's happening in here. Okay, so basically we spawn a thread and wait for it. But it's important to talk about the refs here, because that's what we need to change now. Because this is not, we can't call these instructions again, and that's the issue. It would be fine if this was the whole program. This is fine, but if we put this in a function, and we call the function, of course it does work now, but now we can see that now we have a function call that we do instead. Well, it's still the fork, but it still looks the same, except this changed into a function call instead of an exec thread. And then if we look at the actual thing down here, it's like we are creating so this is a block as well. So we're creating a block. Maybe we actually could remove the block, because it actually complicates things a little bit. Now you can define a function like this, and it should still work, yeah. Which basically is kind of like a inline definition of the function, or it's more like this part, the thing that comes after the return type or the standard out type is an expression. So you can have any expression here, which includes just echo hello. And if you happen to have curly braces, that just means that you have a block expression. But this results in an easier to read here thing. So here is the function body, which is basically just consisting of this that we had before. So we have exec thread ref, we fork it, we wait on that. But the problem with these refs are that this address is like hard coded. So if you call this again, you will get the same address, the same name and everything. So it's like we call this again, and now of course we get an error. We do execute the first hello, but when we come to the second one, so here's the main program. We call here, this is the first call, these three things here, and then we call it again down here. And when we do that, we will get, well, let's look at this. We will ref this again here, the execution thread again, which will cause a duplicate ref issue. And the way to solve this is to have these refs not be comtime known. So these addresses will not be known at comtime. Which means, yeah, as I said, it means that we need some sort of runtime memory allocation mechanism. And that's what I'm trying to figure out. But I just wanted to show how this could work. But let's start with looking at this here. So as we saw in here, let's just copy this. So we have these three things, and then the execution down here. So I'll just copy that. So this is the main program, and then this is the executable, like echo hello. I'll just delete this. All right. So we'll ref exec thread. We'll fork it to the other thing. This is like inherit. I'm just gonna call this inherit. We fork it to exec echo hello. We wait for exec thread. Also, this is stored in exec thread as well. And then here is the closable process. And we'll wait for that. Exec. We push the executable context. So that's basically what's happening here. This is like a simplified version of the thing here. So we're creating kind of like a variable, a global variable that is named exec thread, you can say, almost. And then we fork and we store the result, like the thread handle, in exec thread. What we're forking is we're forking a new thread that will start over here, and we inherit the kind of the context as well of the main thread, and then we wait for this for the thread to complete. Okay, and then in this thread we create a ref for this closable process. We push some execution context, and then we call execute, which will pop this and run the executable, and it stores the process ID, you could say, in this thing, in the handle, and then we wait for that process to end. So that's what's happening here. And we need to figure out now these refs, how to kind of make instructions, or upgrade the virtual machine to somehow be able to dynamically request memory places to have, and also probably some kind of garbage collection idea for that. We might just make a leaking version first and then add garbage collection later. We'll see. Hello Crimson X, what's up? Well, it randomly showed up my feed and I'm interested. Can you kind of tell me short what this is about? So basically what it says on the tin, like, if you're familiar with Bash, I'm making a Bash kind of like language. I have these two comparison files, which I usually use to show here, and kind of like test suites to see that everything's working. And so it's kind of used like as a comparison here. So on the right hand side we have the Bash script, which is just a normal Bash script that is, like, to the best of my abilities written here. And then we have the left hand side, which is my new language called Runic. So it's basically gonna be sort of working as it's like the project is kind of like it spawned from me not wanting to learn Bash, basically. So I decided to make my own language instead, which does the same thing, except it has like different syntax and other features probably. So yeah, that's basically it. And then the pipelines are gonna be sort of the same, calling like executables, but then all the programming stuff, like if statements, for loops, binding, creating variables and stuff, that's gonna be more like have a zig-like syntax, which is a programming language that I'm using to create the language. So yeah, that's basically it. So what I'm thinking here is that we can still use the refs, but instead of them being like comp time known addresses, they would be simply placeholders I guess. And then in runtime, what would happen then? Like we create a new ref. We execute the instruction. That would not only declare the ref. Well, it does. I don't think it's actually doing anything right now. The evaluation of the ref instruction, I don't think we actually do anything with that. Or do we? We check. Okay. So So actually we do grab it. Like we grab the location where it is, and we see if it already exists. So that's a duplicate ref if it already exists. So that's the error that we actually get. And then we also set the value of this location to null. So the memory location set to null as well. Or I mean it's set to void. And then we simply continue there. So yeah, that's what's happening there. So basically not much is happening except we do like a duplicate check and we set it to void. But I think what we would want to do instead is to create a new ref instead of trying to find based on the address here. We create a new address that we would like to have to use. Yeah, that I think, yeah. So pardon me, I'm not too familiar with tech, but what I caught on is you're making a shell scripting language using a programming language called Zig. I assume Zig is like C. Yes, basically. Yeah, so Zig is like a modern take on C, you could say. It's low-level manual memory managed language with some new fancy features, and yeah, I'm making a shell scripting language, but it's not gonna be like a new shell or anything. I'm not sure what it's gonna end up being. It's more like a personal kind of hobby experiment, but that may become something in the future, but we'll see. I'm just trying to make it work right now, and then we'll see how much I will do with it later. But I will I'm gonna make it until it's like, for me, replaceable with Bash, or Bash becomes replaceable with Runic for me personally. I mean, there might be features in Bash that we are not gonna have or something like that. I'm not sure that, you know, other Bash like programmers are using. I'm just gonna get it up to speed to where I'm you know, can use it without any hassle, and then we'll see if I'm gonna like continue adding more things to it or something like that. But yeah. Are you using .zig? What do you mean? I'm using Zig for the making the language, and then the language itself is written in .rn is called right now. But I mean, that could change as well. I don't know. I just chose .rn as like a quick. I don't think I did check if something else used it, and I don't think that was the case. I'm not 100% sure though. The thing about the ref though is like, how do we... It's kind of like a scoped variable, but yeah, the thing is like the ref is weird right now. like, I'm not sure how we create this, let's say dynamically this address here, and then how do we identify the ref later? I think maybe we need both the compilation, the compiled kind of ref number, to be able to uniquely identify the ref, but then in the evaluation, it would also be kind of a local thing as well. Because what's gonna happen, like, if let's say we jump up here, let's say we have a label here, and we jump up to start. What editor is? It's NeoVim, yes. And then we create a new ref, but where is that result gonna be stored? Maybe we need registers now. Or maybe it's going to be pushed to the stack. I mean, it's either going to be a register or we push it to the stack. We have to kind of change the context somehow, I think. And then here we don't actually use refs as a location. We have to use the stack now. Yeah, we just push it onto the stack, fork, wait, and I guess we'll pop it later. And then this would be, you know, instead of being like a ref, it's more like a stack instead. Well, we kind of lose this label here, so we don't really see that this is what we're waiting for in the instructions. We're gonna see like stack instead, unless we can somehow map that later. But what if you have like multiple, you know, 1, 2, 3, like how would we know which ref is which stack? I mean, I guess we could maybe store like a relative stack. No. I mean, maybe, because in this context, like this is one compilation. This is like compilation unit. So each unit would know that we're not pushing a bunch of stuff. Like if you push something to the stack, you have to pop it later. So we're always kind of managing that. So we should know that calling this won't really mess with the stack, so that we can't use it anymore. So we could potentially say, let's say we have two things here, and then we want to fork this. Let's say we have something like this, and that will mean this points to, this really becomes like push, you know, push. Yeah, this pushes some kind of allocated address And this also pushes allocated address. So this would be like stack. Let's just use a random number here, 4, and this would be stack 5. Okay, so then when we come down here and we see, okay, we got the ref exec thread. Okay, so what does that mean? Well, we could store here a relative stack based on how many refs we create or how much we're manipulating stack. Basically, we could store that, well, this should be like the stack pointer minus 2, basically. So what we the kind of value, the address that we store in the ref would be like the relative stack based on where it's going to be used later. But actually down here we could have a different stack relative number though. And it can't be, of course, it can't be like an absolute stack because we don't really know. Like in this compilation unit, we wouldn't know what the absolute stack is. And of course we need to pop again. Okay. So then is it enough for just having like the relative stack? I mean, maybe this ref, when you're actually passing a ref like this, it has both like the ref. Yeah, we just pass the ref ID so that we can get the label, or just the ref label itself, and the relative stack of where it should be. Yeah. Actually, this could just be a labeled stack address. Okay. So a ref is like a labeled, maybe like a labeled address. This could be like a global address, actually. No, it can't. It has to be like kind of like a relative stack address. Yeah, it has to be. It has to be a relative stack address. So this would be like actually it's gonna be negative, yeah. Okay. Yeah, now we have a whole bunch of stuff we need to change. All right. I'm not even sure if we need refs, actually. These are gonna be like, we don't need a place to store the refs. They're just gonna be put in the instructions now. So we're not actually gonna have this here. So I think we can just remove that. Yeah. And the new ref will not create a ref like this. We will create name is going to be name, and the address, yeah, is going to be that. So we have to kind of pass this in here. Yeah. And then here, the instruction itself doesn't actually need a ref. The instruction is just gonna be this, because it just means it's basically push, except when we use this in the compilation, we use it to label the stack. A labeled push. Although we could store the name here. We could store the name so that we can format it. When we format the instruction, we see what oh yeah, so ref, so this would actually be over here. Whoops. Ref and then S instead of F. Yeah. Let's review race. What? What do you mean? Alright, so now we have a whole bunch of places we need to fix. Oh yeah, is waitable. What do you actually do? You check if it's an ad, right? Right, what are you doing? We're creating a location. All right, because we are assuming that the value we get, the address we get is a ref based, but then we don't have the address here. I think this changes a lot of stuff. Maybe. Because if we're gonna use the stack and we want to return the ref, how are we gonna return the ref without, like, how are we gonna return the ref? Like, unless every time we return something, we assume that it's pushed onto the stack. So for example, in like compile if, we have, I mean, just a simple thing as an if with no else, this would be a result. And here we can see that, yeah, we have we're creating a ref. Now before we could just create it and return it because the address was known at this point. But now what we need to do, what do we need to do? We push this on the stack, and at the end, and then other things would kind of, you know, populate this. So this is kind of like a local variable now. We're creating a local variable which gets modified later here, and then at the end we need to kind of return this local variable. Actually, we just don't pop it then. What the hell is happening? My keyboard just disconnected for some reason. Okay, let's say that we return that. I mean, it might be that we don't need to do a lot of things, but I just need to make sure that everything is, like for example here we're using this result. So what is this result? Now this could be a comp time result, or it could be a ref result. But the problem here is that if this is a ref result, that means we've now pushed something onto the stack. So over here, how do we, like, when we're consuming this value here, we actually do need to kind of handle that case. So it's like, yeah, we get this else here. Also, how would we know now what this result is? I think this is just going to be like, if this is a ref, it's gonna be like because the only thing left on the stack should be this, like in this context, in the context of this compilation, the only thing left on the stack is this initial ref push here. So we could just return this ref as because the thing is that this doesn't really return a location. I mean, what would this actually be here? This would be like 1. I mean, it depends on, yeah, it's like it depends on where we use the ref, not where we create the ref. So this doesn't really make sense. Yeah, this doesn't make sense because here we just need the name. So we don't even create this over here. We don't even do this. We just need the name. And then we don't even get a location back here. I mean, I guess what we could return is the name itself. That's the only thing that we kind of need to create the ref later, I guess. man. Oh god, oh man. And all right. I'm just gonna refill my coffee. I'll be right back. All right, let's see if we can fix this. I mean, it's gonna be a lot, but it's like it's gonna be so nice when this is done here. It's good. It's better to do it now when we than later. Yeah, I should have done this before. Oh man, why is the man? My keyboard is like malfunctioning. What the hell? Alright, I'll try to connect it to a separate port. There we go. That never happened before. That's weird. Alright, so what do we need to do here? So yeah, so this is now just a name. So this would be just a way to be able to create ref locations. So this would be a location. Now I'm gonna add a convenience function here if I don't have it yet. No. So we'll add a convenience function which would be from ref. So we'll just have like the ref information here, and we'll return this. And actually we need the relative stack address as well. So this will be a ref name. Let's just rename this to name. And this will be that. There we are. A little bit easier to use this now. So this will be from ref. Now everywhere we have to use the ref now. We have to specify, okay, where is the stack thing? Now the question is the stack counter? No, it makes sense if the stack counter is at the current like unused stack. So we have to go back one. And then we have to make sure that, okay, if we're pushing something else, we need to kind of modify this number here. So that's gonna be how can we fix that? I'm not sure. Unless we can create kind of like we can create like a compilation unit struct that would keep track of kind of the local stack counter. If you're using, for example, things like push and that, we could do that. Or, you know, yeah, we're just mapping. Actually, we could kind of do that already. We could, like, because we have all the instructions are used, like we are using these sets and jump, and these functions are like convenience functions for adding instructions. So we could build it into these instructions to actually and pop and all that, to actually kind of modify a local compilation I guess where would that be? Like, it would be like part of the instruction set, I guess. Yeah. So this would be like the stack counter. Yeah, we would be able to, I think we would be able to kind of understand. Or can we? No, not if we jump. Not if we jump. It's the same issue here. Yeah. Although in one kind of compilation unit, you could say, we could keep track of that. Or could we? Like in an isolated unit, if you're pushing something, we could know where that specific push is like relative to something else in the same compilation unit. So for example, so the idea is that I would have a compilation unit, let's say. And then, oops. And then in here we would have the stack counter starts at 0. So this is like a relative stack counter. And then we have those, all of those like functions that add instructions. Here. Yeah, you could do something like that maybe. I'm not sure if it's a good pattern. Because what the problem it would solve is, or if I'm like overdoing this, but basically you don't have to put numbers, like magic numbers in here. It's like if we do, you know, self push something, then we would know that, okay, this ref actually, this pushes 1. So now we know that the current stack number is 1. So if we say here, for example, we say like, okay, well, we have a relative number. I mean, I guess, actually, you know what? Let's do this. Let's do compilation unit. So I'm going to remove this. But what I'm going to do is I'm going to say, let's make a stack of relatives, of like compilation units or relative stack things. So we could just make a stack of this. Actually, you know what? Let's actually keep this compilation unit, and I'm just gonna add a init function for convenience here. All right, and then here we'll have like units. There's gonna be a stack of compilation units. Okay, and then we can add somewhere here. Let's add unit. and we will get a unit back. I guess we get a pointer back. Actually, let's call this push unit. And this would do units append init. And we will return the last item. So we push a new unit, and then we can pop as well. So that would do nothing. We'll pop. So basically, if you need refs now, it's like you can push a unit, and also I want to get the current unit. Whoops. Actually, we don't need to return this here. We don't actually need to do anything there. But we can do this, so we can return self units items self units items length -1. That is the current unit. Okay, and then we're kind of asserting that we already have a unit. So actually, when we compile, we should push a unit. So we're gonna do like push unit and then defer pop unit, so that we always have a unit if we need to have one. Okay, so the idea is that we would, like, when you let's say you compile this if thing, first, since we're using refs now and we need to kind of talk about the relative stack, we're gonna do try self push unit, and then we defer pop unit at the end. Okay, now what we can do is we can say here we can say like dot ref location, or not dot, just ref self dot ref location result, and the ref location will be a function that takes a name and creates a location. And so here we would return from ref name, and then this would be oh yeah, but now we need more information. Okay, so actually when we do new ref, we get like so what we need to get back is not only the name, but also kind of like where the relative stack pointer was when we created the ref. So it's like we need like a ref info or something, I don't know what to call it. Definition info, I don't know. Ref def. That sounds cool. Okay, so that's a name, and then we need a relative stack address. So that's the relative stack address when this was created. And then we return name is name, but then the relative stack address is going to be self current unit relative stack counter. Okay. And also, since we're creating a ref instruction, that means that we also the virtual machine will push at this point. So what we're doing is we also defer current unit relative stack counter to increase as well. So now we can keep track of where the relative stack counter is at all times. It should also happen in push. So self current unit plus equal to 1. Push location is also doing that. And pop will do -1. And then there's also exec, which also does that. So exec will actually modify anything that modifies the stack. Yeah, you also pop. Maybe we should make it simpler so that we don't bake that into those things, but I'm not sure. I don't remember if fork does push things to the stack. Actually, I think it does. I don't think it pushes things onto the current stack though. It pushes things into the new stack. So we create a new, hang on. We spawn a thread. Yeah, we're pushing into the new thread stack. Yeah. So that's weird because we don't really have that context actually. Oh shit. Oh wait. So actually the compilation units are per instruction set. Yeah. Not per the whole compilation. It's actually gonna be here. So this would actually grab the current instruction set. Oh. No. Okay. Current instruction set. Gonna be a pointer to instruction set. Return self. Oops. Instruction sets. Self current instruction set. There we go. So this is current instruction set. There we go. What? Okay. Right, back to this. You should return a refdef. Now. And you're gonna be the refdef. And the relative stack address is gonna be ref. It's gonna be like current unit minus this. So there we go. That was the idea. So basically, yeah, we have this unit thing. When we create a new ref, we store the current like relative address, stack address, and then when we use this function, it calculates what the relative stack address would be here. So we don't have to kind of make up all of those. We don't have to kind of manually calculate the kind of relative stack number here, which is very helpful. Now I'm not 100% sure that this will actually work, but I guess we'll find out. Compile expression. Yeah, so even if, let's say this now pushes something and then it doesn't pop it, we still know within this unit that it would have changed its thing. Although I'm actually not entirely sure if we actually want to create a unit here. Actually, you know what? When we pop a unit, we get the popped unit out, and if this unit, this has to exist now. If this unit has the relative stack counter being positive, that means we haven't pushed. That means we have pushed more than we have popped, and that means we should actually kind of modify. Actually, no, it shouldn't always exist. If it doesn't exist, we return. Yeah. But then we should have. So we pop that. Now let's say we have if get last units. I wish there was a way to do this and get the pointer. Can you actually do this, like pointer to that? Last or null, and then this would be the unit. Right? Would does that actually work? Because this is like returning a constant. I don't know. This feels kind of magical. This is like, I'm not sure if this actually works. I guess we'll find out. Like, what is this pointing to? But it does say that it's mutable, so it doesn't say that it is constant. So it might actually wire it up correctly here, which is really nice, because this is a nice way to be able to get this here. So, so if this is non-zero, it means that in this unit, what we need to do is we need to add this here. Yeah, so because, yeah, now, and then that will carry over now. So if you have a sub context that pushed more than it popped, then now we carry that over. So we still have the correct relative stack counter. Yes. So now we're safe to do this here. So, but because if this, let's say this compilation here pushed like more than it popped, So now the relative stack counter here should be more than it was over here. So this unit would now carry that information as well. So that's good. Okay, so what are we doing here as well? Well, we have this condition. Yeah, the problem here though is that the result can actually, like, let's say the result is a ref. No, it can't. It has to be anything that gets returned will not be a ref. It will actually be like a it will be the stack thing. Yeah, from a ref def. So this would then be, this could be, this is a ref def here. Yeah. So if the type is a ref def, which of course now we need to put down here somewhere. Then it's a location, but it's actually going to be like a stack. Well, it is a ref though. And actually it's gonna be like self. Oh shit. Okay, now we don't have the context anymore here, so I was thinking like, okay, do we have to move this function now? We could also just do this. Well, we know that this is a ref def, so we can just say ref location ref def for result. Yeah. Okay, and the set, same thing here. This is now a ref location as well. Okay. Now, of course, this pattern, I'm not sure how well this is going to work. Like, let's say we're in a for loop. It's kind of like you have to put some constraints on it. Like, yeah, we can refer to this ref probably here with no issues. Maybe. But we do have a jump here. But this jump, it only moves forward. But it does skip compilation. So basically this part here does change. This could change the yeah, this could actually okay. So maybe this is flawed. We have to kind of figure out, okay, what does this mean? So the jump will jump to after if the condition is true or false, I mean, and then we have the jump. So let's say the condition is true, then we execute all the, basically we execute all of the expressions, and then we should be fine. However, if we jump to the after, that means we jump over here, which is just, you know, it's just gonna return the afterwards. So but we do have a ref location here. So what does this ref location mean? it's like it's going to be different between if we run these instructions or don't run these instructions. The relative stack counter could be different. So, or could it? That's what we have to figure out. I mean, there might be a way smarter way to do this. Yeah, there's like stack frames. There are stack frames as well. That now we're talking about a new relative kind of number. So what the idea is that you push a stack frame here, or well, you set the stack frame. Wait, no. How does it work? You just set the stack frame register to the current stack counter, and now you can kind of calculate based on the stack frame where your stack variables are. Or is that really what it's used for? I think it's like, how would that work like recursively? Or like repeatedly? I mean, we could also try and solve it by just introducing register, like a return register. So that means that every instruction is not gonna, like when we compile this, we always know that the stack counter is actually gonna be restored to what it was before. But that doesn't really solve the issue either, but because... No, yeah, it does solve the issue actually. Because then this couldn't modify the stack. This doesn't modify the stack. And so down here should still be correct. Because the thing is, like, if we use return values as like stack based on the stack, then we wouldn't really know if this becomes, if this is a stack or not, unless we check it. We have to check what then would be, because it could be like a comp time. It could be a comp time result, but it could also be something pushed onto the stack as well. I guess the same is true if we want to use... No, I'm just trying to figure out, like, maybe we're going about this the wrong way. Like, instead of using the stack for refs, we could also use Some kind of like allocation there that I was thinking first. Yo, Penguin, welcome back. What's up? I'm kind of staring myself blind at this right now. So what would we do here? Let's say yeah, the issue is that every time we like compile an expression, if the stack is not restored, we don't know. We kind of lose the relative stack information because we're skipping these instructions. And now this relative location is not the same. It depends on the condition. And I mean, we could perhaps no. Yeah, I mean, we could do like a very ugly spaghetti thing here where we have two result things that we actually do know the location. So it's like we have then no, here we do know the location, yeah. But the problem is over here. Yo, welcome back, Code Guy. Yeah, I mean, it's going good, but it's now we have some tricky, at least for me, like tricky stuff to figure out here in the kind of like assembly like code here. How are you doing, Code Guy? Why did you stop driving? I just checked my phone. Sorry. I'm in a place now where I need to kind of reload my brain a little bit, because this issue here is like it's like wrecking my brain. Like I'm not used to doing a bunch of kind of assembly like stuff, or compile. I guess I should say more like compiling. Yeah, making an IR basically. Yeah, so the thing that I'm doing right now is basically, it's kind of hard to explain. It's more like how the compilation worked before was wrong basically, and now I'm trying to fix it. I can tell from your videos. What do you mean? What can you tell? But we're here to learn and have fun. I think it's extremely, I mean, it's extremely satisfying getting it to work. But I just need to figure out how to do it. It's like a puzzle, solving a puzzle. I know it's possible, you know, but we just need to figure out what to do. Okay, first thing that I'm gonna do is I'm gonna separate this a little bit so we can see more what's going on. Okay, you're like initializing that to void. Why do we even do that? That's done anyway in the thing. Yeah, we don't even need to do this. I'm gonna remove that. And then we have the condition. We're creating a new label after address. We have the jump instruction, which jumps over then. That's after. Oh, I see. That's fine. Yeah. You should enable the live CC. It's a good feature. Live CC. What? I'm not sure how to do that. I don't see any settings. What the hell? Yeah. I've like enabled everything that I can see. I don't know. Maybe it's not available. All right. Yeah, because let's say you have the stack frame counter. What I don't understand about the stack frame is basically if you have another thing that pushes another stack frame counter, then how do you restore that, the previous one? I'm just gonna look at this here because it could be the solution. I'm just gonna. Sorry, this is we're gonna get bright here. In 1, 2, 3. Boom. Cost stack frame. Frame data. Yes. No. Local variables. Let's go for a single function and setting a function. Yes. The question though is that how would you know where it is down here? Stack pointer puts to top element stack. Man, this this diagram, man. Okay, parameter, yeah, stack frame function 1. Yes. Any return function return condition is satisfied. The return will stack with a stack frame. These any recursive function get base condition satisfied and return. Put a return after base condition. Base condition will not wait for to load like a variable located in else part of the program. It will immediately return the current frame from stack, following which the next frame is now the activation record. Right, so here we have a bunch of variables as well that does not get done anything with. And we have a bunch of frames. Or, yeah, the allocation of the blocks now. Yeah, that's also something like if you return like early from a function, you don't pop, like it's gonna restore the counter back to the frame as well. But the question is like, what if you call another function that changes the frame register? Yeah, okay, so we call hello, right? Yes. That creates another stack frame. But is that also like put on the stack or something? Like, where is that stored? Like, how do you know? I know there's a register for it in x86 64. But that's not a stack. Does it restore that after the call or something? I don't know. Right. So BP is... Oh, it does push the stack frame, okay. Oh, it pushes the previous one. Okay, so we push... We store the previous frame. And then we overwrite the register. And we allocate some stuff on the stack. And now we're using this register as a thing. Okay. The motivation is that there's basically two major motivations. The number one is I don't want to learn Bash. And number two, well, okay, I'll expand on number one. But number two is also that I want to make a language. And I think it's fun. So to expand on number one is basically... I kind of want to learn Bash, but I don't want to have all that different kind of... Like every feature in Bash has its own syntax. And I don't want to have that in my head. And the consequence is that I constantly have to check how to do things in Bash. I constantly have to check, okay, how do you do an if statement? Just like, where do you put the semicolon? Where do you put the then? Do you have a then? Yes, you do. Like, do you have a semicolon before the fee or after the fee? Or, you know, it's like all these rules that are basically seems to change between each feature in Bash. So that is why the kind of frustration of that has built up, and I just said, hey, I like making languages, so I'm just gonna try and make my own Bash language. But it's more of like the act of actually making a language itself which I just find like a fun experience. So yeah, that's that. All right. So, okay. So actually, what we could do with these things is that we could we could say that this would be, let's say that this is a frame instead. Let's call these frames. Let's call this like stack frame. There we go. But the thing that we're missing is a register. So if we go to the IR context, we can see that we have a shared context. We should be like here. Here's kind of where you could add register. So we have an instruction counter, and we have the stack with kind of like a stack counter, because the stack counter is kind of the current, you know, the current length of this dynamic array. But then we could, I guess we could also add like a stack frame. Here as well. So that would just be a usize, start at 0. So that would be the current stack frame thing. Okay. Now I know I've cheated a little bit by doing this. I knew kind of why. I knew kind of how it worked, but no, also not. But it's like, yeah. So I kind of cheated a little bit looking at how C does it. But yeah, sometimes you just have to give up and read a little bit. Okay. So when we push a frame, we could also say yes, that is basically it. Should be in the OBS. Really? Okay. Okay, well, I don't know. I'm not gonna check it right now, code guy. Okay, so when we push a frame, we also do add instruction. And then you need instruction type, of course. You are going to be push something. So you are just a value. So we're pushing. Actually, this would be like a location, actually. Yeah, this would be like a register reference. We don't really have that right now. So yeah, I mean, let's just do like register. This is like an enum. I mean, we could add like, you know, instruction counter, stack frame. I'm gonna call it SF, stack counter. We could have these as things like that. It's just whenever you have registers, you have to have short, undecipherable names. Okay, so now this would be a register, and this would be the stack frame. So we're pushing that. And then when we pop a frame, I guess what we do is we pop the register. The thing is, we don't have a place to store this. But I guess what we could do is we could say, we could set the register so we need location and value. So location is going to be a register, and that is going to be the stack thing. And then the value is going to be also a location. Well, actually, it's an address. I forgot what we had here. If we had like from address, right? But we need to kind of convert the address. So this is like from address. Hang on. Yeah, this is gonna be like stack counter -1 basically. Do you have prior experience in doing something like this? Not exactly this, but I have experience in making like a compiler to assembly. Not like a advanced one or anything like that, but I have programmed a little bit in assembly, but not, you know, any large project or anything like that. But I know kind of like the basics, and I've never done like this advanced of a compiler to an assembly-like language before. Yeah. But I have, you know, dabbled a lot in different things. Yeah, so I know also like in modern kind of architectures, you have like when you can, like in assembly code, when you kind of, let's say you want to set an address to something, now that address could also be calculated from like a relative, where you can have different modes. So you could have like, let's say you, like which address you're selecting could be an absolute address, or it could be an absolute address that also includes like plus something, like plus some number, and even times some number as well. So it's like you can do a lot of things in the like instructions in assembly code, and I'm thinking we should probably have something like this here. Like you could say that, okay, well, I want to take the like in the location address, just to avoid having to write to like another register or something. We would take like what is the current stack counter and take -1 from that. So for example, here is like, well, now we have from address, but actually what we would want to do is we would want to say like location to address. Well, actually this is like stack no, wait, what the hell? Yeah, it's like a relative stack address. No, this is gonna be like the register of stack counter, but it's also gonna be an arithmetic thing. So it's like we also could provide add, let's just say, an add would have a location, except we can't because that's recursive, and now it's all like well, we could do a similar thing we did in another place. You could have like all of these are kind of like absolute addresses, and then you can have a modification. So actually a location would be a struct. So this would be a location, this would be like absolute or something, and then we have the location is a struct that has the absolute location, and then the modification, so location mod which would be some kind of modification. So let's say we have like add some kind of number sub, you know, so you can do a whole bunch of different things there if you want. So now we're taking this address, and now we can, if you have something in mod, you would also like do that. Now we could set this to null, I guess. And yeah, and then let's add this over here. Yeah, I like using this because it's like just because of things like this when you want to refactor or like copy stuff. Also, I'm gonna move you up here. Okay, so we get abs. Now if we have a mod, we get that, and we switch on that. And we have like add. There's gonna be, you know, we return that sub. And I guess, I mean, it's gonna be kind of a fatal thing. If you sub something beyond 0, that's gonna be bad. So I'll just do that. Otherwise, we would return just apps. Yeah, and then there's also usually, like if, let's say you want to iterate through an array, then assembly also has another thing called, like, I'm not really sure what it's called, but it's like you can have a kind of like an iterator number and then a multiplier. So then you would have both, like you're adding another term which is like I times the size of the item in the array, but I don't think we need that right now, so I'm not going to add that. I don't know how long you've been doing this, but at any point did you think of using AI to help you in that way? Yes. That's kind of how I started out with this project. So basically the foundation of the project at first was built using AI only. So I never actually touched the code at all, like when I first started this project. So kind of the initial version of the project was all AI. Until I wasn't very good at directing AI, I would say. So in the end, the project was like, it was extremely like fragmented, and I told like AI to, hey, could you add this feature? And it was like, yeah, I can't do this feature because I need to do this first, and then I need to do this first, and I need to do this first. Okay. And then I said like, okay, well, could you start with doing the first thing that you said? And it was like, no, I can't do it. So it's like AI kind of gave up. And after that point, I just took over, and I haven't really used AI much after that. I've used it for some things, like I think there was one bug that I used AI to kind of search for what the because I think that's a pretty good use of AI. It's like you have to kind of learn how to use AI. Like it's really good at certain tasks, like boilerplate tasks, or like for example, I used AI to add a bunch of logs to one of the sections in the compiler, and so I added that, or in the one of the things anyway in the program, and it's also good, like, yeah, just boilerplate stuff, scaffolding, documentation, doing things like that, things like, that it's not gonna be hard to do, but it's gonna be tedious and take a long time to do yourself, or to find, could you investigate where this bug would come from, and it could do that while you're doing something else. So that is that's what I have found is a really nice use of AI. But it's also like I have to think about, it's like having to think about what your coworker like should do at all times. It's also like taxing like that. So I basically I don't really use AI much in this project anymore. But I am trying to learn more about how to use AI for the future, and also for like in my day job as well, which is really nice. So I was recently learned about MCPs, which is really nice. Extremely interesting way of doing things. And yeah, so that's why if you look at the project, if you look at the GitHub right now, it's like a lot of the documentation, a lot of like things that are in like example folders, a lot of the code is still like created from AI from the start. But then I kind of taken over from there and yeah, started implementing things myself instead. So yeah, there was no IR stuff before, like when AI did it. It was everything was just I don't know. I didn't really look much on the AI code. I just scrapped basically a lot of it and just continued doing stuff for myself instead. But yeah, it's like, but also it's like when you're using AI to do something, it's like the things that I want to use AI. It's not like if I could, let's say hypothetically, I could say, hey AI, could you do this project for me, and it would just do it. That wouldn't be fun for me. It's like I want to do it myself. It's like I want to solve the problem myself. Like that is part of the kind of, I have programming as a hobby. Like I do this for fun. So that also plays in here. So even if I could ask AI to do everything for me, I wouldn't. I might do it for other things, like other projects, but it's like it depends on what I want to do. All right. Now we have some issues. So format, yeah, I'm gonna also forward the format function. No, not self, right? Print format, and this would be self.abs. And I guess if we have mod, actually let's do two different branches here. So if we don't have a mod, we'll do this. Otherwise, I think usually you have something like something like this, and then it like depending on what the mod is, we would do like if it's add. Oops. I mean, I guess we could do like this. So let's do it format for the mod, and then yeah, that's actually just the format of the mod. Yeah. So then this would be the mod. Have a space there, and now if we go to mod, we can add a format function here, and we can say switch self. If we have add, we're gonna write writer print. So we're gonna do like plus, and then here, and sub, same thing, except it's going to be minus. Yep. All right, cool. Okay, so now we have that. And now we need to adapt a whole bunch of stuff, places, things. Right, so this error, sure, let's move it in here. And then you have like, you're gonna be locationer. register. You're gonna be, I'm just gonna say R. And I guess this would be the tag, because it's like, it's just an enum. And usually I think, well, you could like percent, that is one of the conventions, like one of the assembly conventions to use percentage for. I think it's like Intel versus something else, I forgot. Like, what's it called? Formatting for assembly code. Okay. Right. And I guess these frame things, I'm not sure if we even need these, but I'm just gonna have them, I guess. We'll see. I'm trying to figure it out here. No field named register in value. Okay. Pushing a value. Yeah, that's right. Let's do like. Okay. Yeah. Because that's gonna be like an address. No, so the value could be a. I mean. Yeah, the registers are not, they are not addresses. Okay, we'll do this. I'm just gonna add register here. Actually, you know what? Let's move it. No, okay, fine, whatever. Register. I was thinking of moving it into location, like location dot register. All right, cool guy. Deserialize. Okay, sure. Serialize. Okay, I'm not even sure. I don't think we even use this much for things. But I guess we'll add this here because. Right enum. Wait. What? Wait, so why is there like a take enum, but there's no write enum? enum. How do I get the enum? I guess type info, type of, or enum. Tag type? No. What? Yes, maybe? I guess we'll find out. The error list keeps growing. Okay, yeah, this was way larger than I anticipated. Right, so we have the registers as a value. Take enum error. Okay. Yeah, there's a lot of changes that's gonna happen here. Register is doing that. I'll just do this. Okay, so back to what? Back to like push frame. Yeah. Or actually it's no, it is here, right? No. Yeah, okay, so now this is a value, so that's good. So we can have this as a value, kind of. There we go. And then we're popping wait. So yeah, the thing about pop, like in assembly code, pop actually gets stored somewhere, but now for this language it's not actually stored anywhere. We just pop, like we just change the stack frame or the stack counter. So I'm gonna put pop after here and then before. Well, I guess it doesn't really matter. We can put it before, I guess. Or can we actually? No, we can't, because that's going to be an error. Are you following any books or online resources, price specifications, building a language like this, or are you figuring things out on the fly? I'm figuring things out on the fly. I mean, it's kind of like mixed, but I'm mostly figuring things out for myself. And I have sometimes people help me. Like we had a couple of days ago, we had a person who was very knowledgeable about the pipelines in Bash, and that helped me with an issue with why grep was behaving weird. So yeah, so it's like a mix, but mostly I'm trying to figure out for myself. Okay, so here, because that's the fun part. It's like I'm trying to solve a puzzle. It's not fun to just read the solution. Like part of the fun for me is the problem solving and actually figuring out yourself, not just read, you know, a solution and and try to copy it. But if I get like super stuck and I need more like ideas, then I would go out and look at other things. Because I do want to also get this completed at some point. I don't want to just get stuck and then give up, you know. So I guess it depends on my patience. I don't know. But yeah, I kind of feel like, okay, but now I'm nearing the point of, okay, now I'm kind of like, I was sitting with the problem for a while and I can't find a solution. So, okay, let's just do some research. There's probably a whole bunch of books actually for this, but... And I might go and read some, like, if I do like after this. But as I said, like, part of the fun for me here is like figuring out. And there's always new things to learn, like, yeah. Which is part of the fun with programming for me as well. It's like you can always find new things to learn or invent things. Like even if you know everything there is to know right now about programming, you can still invent more things. No location. Oh yeah, that's the absolute. That's right. Okay, so I think what I want to have also is like I want to have like init abs, which only takes the abs, and well, actually, let's just do like init. And then, no, that's fine. Wait, where are we? Here. So then it's like init. Okay. So this would be, well, for stack we wouldn't ever like add, I don't think. Well, I mean we might. Actually, no, we do actually for stack frame, like relative to stack frame we would add. But here we would actually just subtract. And we would subtract. Actually, you know what, we could do a convenience function for that as well. We could do like init add and init sum. Yeah. What the hell? So, no, wait, this is not correct. This, well, okay, this is where we want to have that. And the location that we want to change is going to be the register. Although the register doesn't make sense to have like an add to that. No, but whatever. Let's just say that, okay, well, the thing that we need to change, that we want to change, is going to be the register SF. The value that we're going to set it to is going to be a location. Oh shit. Yeah, is this register here doesn't have capability of add and sub now. God damn it. Do we just add? Because I don't want this to be a value type. It does make sense for register to be a value type because the register is not an address. But then we also like... Okay, I guess we'll make a register that also has... Like this is register... I guess this is register absolute, and then this is register with a mod. And then you are absolute. Yeah, that's exactly the same. We could just copy this in. Since we named everything this and we kept the same name for everything, so great. I guess we also need a format function. Yeah, I guess that would be the same as well. We just format the absolute, which also has a format function. Actually, no, it doesn't. It should be T. The register. I mean, the mod itself is like taking the value of this and then adding or subtracting or whatever. Yeah, that's fine. Okay. No, compiler. Here we are. Okay, so now, well, we go to the value and we'll add, instead of register, no, it is register. Yeah. Yes. Okay, and now we do like dot register is this. Okay, so the value of what that, so this instruction, we set the stack frame counter or the stack frame register to this value, which is the stack counter -1. Okay. And we just need to add support for this type of expression in set now, but that's going to be trivial. I just need to figure out like overall the overarching functionality here. So if we think about the stack counter, now this stack counter is now currently, since we're popping here and the popping is actually popping the stack frame, we can reach that with -1. Yeah, that should be good. Okay. And push. Okay, we didn't actually do all this. Abs is register abs, so that was actually different. I was totally blind when I said that. Okay, whatever. Compatible types, location model, use size. Oh, well, abs. It's gotta be abs use size. There we go. And to address, yeah, register is, so scope register is not a supported address type. Oh yeah, ref address. Ref, well, the ref has a relative stack address, but that's relative. To the stack counter, so we can't actually get the address directly from here. We have to have a context here. I mean, I guess we could have the stack. Maybe we'll have like the stack counter passed in, because then we can just say stack counter plus. But now that's also gonna change a whole bunch of places. Actually, it's gonna be negative, I think. Wait, but this might change it anyway. Okay, yeah. Let's figure out the overarching thing first. Yeah, now all this gets changed. Let's back up a little bit. Okay. And oh, this doesn't work. Let's change it back to the error, so we can find this error later. And let's see. Okay, current instruction set. Yeah, put items, that's right. What the hell is happening here? Yeah, that's right, that's correct. Register apps and support. Oh. There we go. Current unit. Frames. Wait. God damn it. Structure set phrase. There we go. Current frame. And out of memory. Oh, now this is an error. I mean, yeah. Cannot assign to constant. Unit. Okay, now we get this issue here. So this is a constant, so we can't actually use get last. I wish there was a version that actually gave you the pointer instead. Yeah, because it's like now we need to say items and we need to say this whole thing. Well, okay. Let's do like structure set. No. If instruction set frames items length more than 0, we will get the frame where's the issue? Is there an issue or kind of hard to tell? It feels like there's an issue because all this is white, which seems wrong. And there's like a syntax error somewhere. Yeah, because this should be yellow here. Oh, you're not a try. There we go. Okay, so it's just a semantic issue. Cool. Yeah. And now pop frame is actually should happen like over here, I guess. Or here, even though it's kind of pointless to have a frame at the top, maybe, I don't know, maybe not. Okay, switch must handle all possibilities. Compile call. Oh yeah, I guess this is like a register. I guess we just forward that. Okay. You're right. So this would be like init absolute. Okay. Let's go back to compile if no else. So, before the return, we do a pop frame. There we go. All right. Now I do realize that it's kind of like, yeah, we're not creating a frame per function call only. Here we're actually creating a frame in the just an if, you know, and we're not like gathering all the declaration, like the scope is because, like, yeah, if you look at C here, and then let's say we have, well, here we have an if, for example. So this if doesn't have its like its own like frame or anything. Let's say we create an integer I here, set it to 5 or something, and then this would be like, or let's set it to 1. So here we can see that it's now we get even more things on the stack, and we are setting frame -4. So that's actually like in my version it would be add 4. But the frame -4 is the where they decided to put this I here. So this, even if this I happens down here, like after the if, it's actually counted into the frame of the function itself. So the kind of the compilation of the function has like a context itself. So where the context is actually the context is created when we encounter like a function, and we kind of compile the function. The function has a compilation context then, which gathers basically all of the like local variables that are in the function, gets put at the top. Basically, it's kind of like there's no difference here doing this. There's no difference in the compilation. Well, I guess, you know, it shifted things around, but basically, but it's like, yeah, it just moved the move instruction. But it's like the point that I'm trying to make is it's still part of the frame of the stack frame. But in my version here, the if compilation also has its own frame now, which I guess, I mean, I don't know. It's like it's maybe unnecessary. Yeah, I guess it's unnecessary. Maybe, like, what about a for loop? Let's say we do like for j. Can you do this actually in C? Yeah, okay. Because I think like in an older version you had to put int j in like outside, like you had to put all of the local variables up here before you could use them. Perhaps, like, I don't remember exactly, but there was something like that anyway. So we do this, and we do like, I don't know, I plus equals j or something, I don't know. So, do you have a stack frame or? how does this work? So J is created. We still have this. I think it might be because of the size. We didn't need more. We still use 32 maybe. I mean, we have 2 ints. I'm not exactly sure. It looks like it's 4 bytes for each int, perhaps. And then this int, so that's like 12 bytes. So we will still push like 32 in here. Because we are storing the frame as well, but that's like before, though. Yeah. See, the leave thing does what I was doing as well. It's like setting the register to the stack pointer where the stack, like the current stack value, and then it I guess it pops it as well. Yeah. And then return will also like go back to where it was. But the loop. Okay, whatever. Yeah, we'll try and figure it out. I mean, there's no like the only thing that could happen as I mean, the thing like we're pushing a frame is like, yeah, maybe it's unnecessary to do it here, but I would like to get it to work first, and then we can look at, okay, how can we optimize it later. I'm just gonna go BRB 1 second here. All right. Let's continue figuring it out. Okay. Yeah, I guess it's like for every scope. Do we need something for every scope? I'm not sure, but anyway, let's just see what happens here. So we'll create this ref, and it's going to be like relative to the stack frame now. So if we go here, yeah, I mean, it's kind of the same thing. Like we're adding this counter, and however, now we can actually return the ref immediately instead. Because, yeah, we can just do this. And then if we go back here, so now we actually get a ref, right? So we still like keep track of how much we pushed and all that. When we, but it's only used for when actually creating refs. So now these refs are kind of like they're more stable, you could say, because we know that in our frame it shouldn't like change. And even if we compile another expression here, we know that the frame hasn't changed, so we can still refer to the same frame. So now, well, actually this would even we can even return a location here because of how this works here. So we can return a ref location instead. Yeah, and there we go. So now we can use this normally here now instead. Oops. No, why did I do that? Oh. Okay, cool. So we're back to that. So the problem was solved by adding a register for the stack frame, adding the frames, the frame mechanism, keeping track of the current like relative stack thing. Although it's still gonna be an issue if, let's say, like up here it's stable, right? But once you're down here, if you're trying to create new refs down here, it's not gonna be stable anymore. Or like here, or yeah, in after here, it's not gonna be stable because we might. No, it is gonna be stable because we don't push more than we pop. Or do we actually? Man. Okay, now we're back to this. I just need to think about if this is gonna be an issue or not. I think as long as you create the refs like up here, it's not gonna be an issue, maybe. Also, you know what? This could be like comp time, of course, optimized. Like if the condition is comp time known, we can actually avoid a whole bunch of things. But I'm just gonna not think about that right now. I mean, it's pretty simple. We simply just check. We compile the condition, and then we check if the condition is an exit code. And if it is, then okay, let's just do it. Then we get like to Boolean. If it's true, we return. If the condition is true, we will return the compile. Well, we will compile the then expression and return that. If it's false, we get down here and we will return compile the. Well, actually, wait. No, then we just return. Yeah, then it's like a void or something. From value void. So it's like if the value is an exit code, this means basically that it was a literal thing. So it means that it's comp time known that this is an exit code. And so we simply check, okay, well, what is it true? Then we just return the then expression. So we don't even, the if statement doesn't even, it doesn't compile. It compiles to the then expression immediately. But if it's false, then we just don't compile anything. Well, we compile the condition, but since it was comp time known, this doesn't actually result in any instructions. So this won't. If we get here, that means that this if didn't actually become instructions at all. So we kind of comp time pruning that away. But okay, so that's done. But we still have the issue down here. So still, let's say we get like a return value here. Like this then expression here could be, I mean, it could be a function call, it could be a comp time known value, it could be anything, basically. And we're setting the result to that value. But what if that was like on the stack? Can we use that? I mean, I guess what we could do is like say that, hey, every expression compiled is gonna be kind of something that gets put on the stack, maybe. That feels bad though. But it could be some kind of convention there, and it could do like, you know, run like compiler optimizations after. But it's basically saying that, okay, well, or we could do a check, like let's say it is on the stack. Okay, then we need to pop it as well. Or another solution would be to add another register that its sole purpose is to return things from inner expressions. So then after this is done, we would get this, so then we know that this won't push things on the stack, and then don't pop it. And then when we set here, this would be this could be like the register or whatever, anything really. And then as long as we use it like directly after this expression here, and then and we pop the frame. So then if we do it like that, we know that all the stack, but it just feels like I know there are operating systems that only work, or architectures I should say, that only work with stack, that doesn't even have, I don't think they have registers. I mean, they need to have some kind of something. Well, I guess technically you could use like the first part of the stack as registers. So then technically you would still have registers. Yeah, okay, let's just do that. Let's just add a register here. So let's add like, I mean, usually you use like the A register to return values from functions, let's say. I'm just gonna say that we're gonna have I don't know, like result register. Okay, so it's kind of implied then that if something needs to be stored in the result register, here we actually don't return this ref. Instead we need to, before we pop the frame, since this is stored on the stack, we actually need to pop this. Pop. And then well, I guess technically we don't need to pop it. If we pop the frame, we should be able to restore. No, wait, we do need to pop it. No, because we could get, technically we could get to the current stack frame by using the stack frame register, right? So we don't need to like pop everything. We can just, yeah, use that. But let's do it anyway. Okay, so we pop the source. Well, now actually we do need to, so before we pop it, excuse me. Yeah, and in assembly code, usually when you have a pop instruction, you also, like in the x86 64, the pop instruction also has a location where you can store the result of the pop. And so doing a pop itself would modify that register, for example. So you could put it in the A register, for example, the racks in a 64-bit system, and it would store that there. However, we're also popping the frame afterwards. So although the frame pop, I mean, yeah, then we could use other instructions. I guess we don't actually have to use the pop instruction. We could set the stack counter register to be yeah, we just set it -1. So location is going to be the register stack counter, and then the value is going to be register stack counter -1. Okay, so now we're not using pop, we are simply setting, which does not modify. Now if we like the term, like want to do it that way, we don't actually, this won't now modify racks, let's say, but this does. And then we can simply say that, hey, yeah, this did pop. So what I'm gonna do is I'm gonna say this would be like result register or location. So let's actually get a location back, and it's always going to be the same location because it's going to be, unless we modify pop to have that we kind of store where it should end. Like we could modify pop to say, do you want to choose where it should store the value. But for now I'm just gonna do location. That's gonna be a well, it's gonna be init absolute register is R for return or result, and then we get the location there, and then this would be from result location. Yeah. So basically we're pushing, this is like it's pushing this on the stack. We're using it as a way to store the result of the if expression. Once the if is done, we pop that off the stack, and we have the result location, which should be the result register, and then in the end we just return that as a kind of like a reference to that register, and we also pop the frame, but this should be intact after this here. Okay. Nice. I think that should be good. Yeah. And then what you think about here is like when you have then here from this could potentially be the same register as this, but it's set over here. So we return this, now then we set, so this would be, now we're kind of using this value, because whenever you're working with like this assembly type code, it's very volatile. Like this, the registers are volatile, so you have to kind of use this value here. Like if you can't use it after the pop, because then it has been overwritten by this, or by the result. So you actually, but since we're using it directly after here, it should be good. So we're setting the result to the register, or whatever this is gonna be. This could be a comp time value as well. And then we pop that, we pop this frame and return it. Yeah, that I think that should be good. Okay. I mean, it's kind of like programming directly in assembly. And then, of course, in the runtime, like in the virtual machine, we have to add a place for the registers to be, their values, and all that. But for now, I just want to fix this part, because this is, for me, the most tricky part right now for changing these things. Like the evaluator later, I think it's going to be pretty easy. The compilation is the hard part, because we're actually like programming the language here. Okay, so same thing here. Let's push a frame. And we do have a source now. So we push the frame, and then this gets pushed there. Condition is, we can do the same thing actually. Let's check the condition first. Yeah, we have to think about the condition as well, because that could be stored in the register as well. So we have to think about, okay, is this also this is also volatile? So we need to make sure that when we compile the expression here, it could be stored in the register. So we may need to make sure that nothing that we're happening down here before we jump is actually changing that register. So, and we don't really do that because we have new ref and new label. Those doesn't really do anything for that, so that's fine. But here's the same thing. So we compile the condition, so now we can remove that. But there's a slight difference here, because this if state expression actually has an else as well, which the previous one only had like a then expression. So we evaluate this. If it's true, we compile the then expression. If it's false, well, we get here, and we can now compile. Now we have to compile the else branch, which should exist. Actually, we have the else branch here. There we go. Else branch and then expression. Is this a union? Yeah. So we have to switch. Do I have compile? No, we're doing a switch. Yeah. Oops. So let's switch on. Well, let's do return. Switch on the else branch. If it's an expression, we compile it. If it's an if, we compile if again. Okay. So that is like the comp time version here. I'm just going to go through this a little bit. So we check the conditions, comp time known. If it's true, we compile then. If it's false, we do else. Compile the expression, or it's another if. Yeah, this is kind of weird, because I mean, of course, the expression could be an if expression by itself. So we don't really need this else branch to have an if. But I guess if we have it like that, maybe we can do some kind of compilation. I don't know, because it's kind of weird, because this if expression is kind of like, yeah, this expression could also be an if expression. So it's like we don't really need to have a union here. We could just have an expression. So yeah, I'm gonna add a to-do here. Check if we really need this to be a union and not just an expression, since if expressions are also an expression. Okay. And by the way, that was AI doing that. Okay, but I mean, there might be, as I said, like it could be some kind of compilation, maybe optimization you could do with that. I'm not sure. If you have like a list of is else instead of like a deep else if thing. Okay, anyway, so that should be good. And then of course at the end we would do pop frame and why push frame, this needs the source, that's right. Yeah, pop frame from result. This would be same thing here, so result location, so we'll do that because this gets pushed over here. We have a bunch of addresses, we have a jump that's using condition, which should be stable at this point. We have the then expression compiled over here. We have set on result, that should be fine. And then we jump unconditionally, I think, to after, yes. And set label doesn't do anything. And then we have the else. That's right, so this now has a thing that we store here. Yeah, okay. All right, cool. So let's do init and there we go. Okay, so now we have a bunch of these errors. So we have this is waitable things. It's like if you return something that is like a thread handle or a process handle, and at some points, like for example after you execute a statement, we want to wait for that to finish unless it's like a async statement. But if it's a synchronous statement, we want to wait for that thing to finish before we continue execution later. So but it's also kind of weird that we can actually check if it's waitable in comp time, but I guess it could be known if we have semantics, but I don't think we really have that too much right now. Like right now, actually the things that gets returned are no longer refs, because refs are stack based. So that's gonna be like the what's it called? The result register. And this was very simple. It's like, yeah, if you return an address, we can wait for it. If you don't, it's not waitable. So it's like, yeah, okay. Now the register, of course, is not an address. So this was like, okay, well, if you return something that is like something we need to wait for, I guess it could be seen as something that has a kind of like a side effect almost now, because anything that is not comp time known is actually gonna be something like a maybe like a function call, but then the function call itself could point to something that is a constant, like you just return a constant. No, but yeah, functions are a bit weird right now. But it's like if you execute a executable, of course that's runtime known only, so that's not comp time known, and that would be returned as a thread handle or a process handle, and it would be stored in a ref. And before that was like stored as an address here, but now we don't really have that. Also, it's kind of weird because this address is like comp time known. So I don't think we're gonna have contain known addresses anymore unless it's a read-only address. But how would we do this now is the question, is what I'm trying to figure out. So I guess it's like if it's a register, but it's always going to be a register now. No, it's not always going to be a register. It's going to be a register if it's something that is, yeah, it's going to be the same kind of logic actually. If it's a register, then it means that we've stored it from popping a ref, which before did the same thing as checking if it was an address. So actually, we now check, okay, well, if it's a register, it's true. I'm gonna keep this as well, I guess. Okay. If it's a register, so that means we're never gonna get a ref here. Refs are never returned like this. So this would, so we're waiting. The location would actually be the result. Oh, yeah. So let's actually remove address, because if it's a register, you know what? Let's actually remove. Let's make this into an optional location actually. And if it's not a register, we receive null. If it is a register, what we get here is a register thing. And so this would be init. Abs is that, and mod is mod. There we go. And now we can simply here, we can say, well, give me the location that we need to wait for. And that's what we get. So that interface is a lot easier now. Although you... Oh, that's a location apps, right. I have to do this. There we go. Okay. Same thing here. There has to be more places that we need to fix, of course, but and we need to adapt the virtual machine to actually work with registers now as well. Okay, cool. Yeah. That's great. Yeah. Okay. Now, I mean, curiously, there's no more compilers in this file, which is surprising me, but let's see. So basically all of these compilation branches, we need to do the same thing here. Like at the end, we have to do this thing here. Anything that could return something is gonna do that, except for this function, I guess, because this is like just a delegator. Yeah. So let's start here. Compile literal. Now this is also, well, actually the string literal can have instructions as well. Yeah, this is an issue actually. Look at this. This is Zig. It is a low-level programming language, yes. Manual memory managed. It's like a modern take on C, you could say. Okay, the issue here is that whenever we compile an expression, we could get a volatile like register out. So when we're looping here, it's like next time we compile expression, we have overwritten whatever is in here. Like this is, if this returns like a register, this will just refer to the register. So let's say all of the expressions return the register, the result register, then all of these would refer to the same register, which would get like overwritten over and over. So instead of doing this, we would have to make instructions that deal with this instead. So this kind of breaks interpolations. Unless all of them are comp time known, then it works. But if like one is runtime known, then it works. But if two or more is runtime known, then it breaks. Why aren't you getting help from Gemini anti-gravity? Because I want to think for myself. No, but yeah. No, I had people in here asking questions about the AI because, I mean, right now AI is going crazy. Everyone is like, yeah, you have to use AI tools. And I do use AI. But for this project, I'm trying to use this as a little as possible because I want to kind of figure things out for myself and actually kind of learn how to do things. So it's like I'm doing this because I want to solve the problem myself. Like I don't want AI to solve it for me. But I am using AI for other things. For example, in my work, I'm using AI to, because I think now it's like, it's also like AI now. It's like I recently discovered that, hey, you could very easily just connect AI to MCPs, which basically connects, you can connect AI to all kinds of things very easily and create your own connections as well. So basically connect it to your repos, your project management software or whatever. Yeah, I mean, I already got the job, and so now I'm just, this is, I'm just doing this as a hobby. Like programming has always been a hobby for me, and this is like I'm doing this for fun. Like I'm making this language for fun. And it's also like if you start to only use AI all the time, you're gonna get so rusty. I feel like you need to kind of keep up. You need to program. You need to practice to like keep with it. I feel like if you go over to only doing AI, you get so lazy. It's like. And even if you use AI to program everything, you have to check what the AI is doing. You have to kind of learn how to work with AI, so that because you can easily, end up with a bad code base if you're using AI like incorrectly. Okay, I'm probably not gonna finish this today. It's probably gonna be, but yeah, the interpolations I'm gonna say to do. Find a way to make this instruction based instead, because of volatile results register. Compile expression in a loop won't cut it. Okay, so I'll just put that there. We still have, it's still gonna work for most cases. It's just if you're, let's say you're interpolating of several runtime values, this is gonna break basically. So unless you're using, well, okay, it's gonna break if you're using multiple interpolations that has like, I don't know, function calls in them or something like that. Then this is gonna break. Okay. Right. And of course, yeah, this is like an allocated stream that we return as a value. So that is also like, yeah, this is actually like an allocated array of values, and that's not, well, actually this is serializable. I think we do serialize this. Yeah. Yeah. So that is storable in the read-only data, I think. But okay, anyway. What are we doing here? So what do you return? You return the, yeah, you return that stream, so that's fine. So we don't actually return any volatile stuff here. Cool, so that's that. The identifier looks this up in the compilation scope, and then we get the result. So that depends entirely on what that is set to. I guess this would all kind of always be on the stack. Like the actual variable would be on the stack. And then the result, the content, would be whatever we bind it to. Yeah. So that should be fine. 100% agree. For tasks you already know are repetitive, it's better to use AI, focus on systematic thinking. Yes, I agree. I very much agree with that. It's very good at like boilerplate stuff, and sometimes if like you know that you, or like let's say you have a bug and you know that you know kind of how to solve the bug. It's just that it's going to be a tedious search for what is causing the bug, because you have you have to go and do a whole bunch of detective work to actually find where the issue is, but you know about whereabouts it is, but you don't. But it's like one of the things that you can do it like 100 million times before, but it still takes a long time to fix because you just have to go through and tediously check everything. That is a very good also use for AI to go in and just say, well, could you investigate where this bug is coming from? Maybe give a little bit of context, and it would, do that in the background while you do some more fun stuff. So that is a very nice actually use of AI actually. But I do think some people are like, they are trusting AI way too much. They are like thinking that AI is gonna solve everything and we don't have to do anything. But I think those people will quickly come to the realization that that is not the case. And yeah, I mean, yeah. I tried, like this project, I did try to use AI at first because I was trying to focus on something else, another project at the time. But then it was like, okay, well, this actually seems like a fun project, and AI did not succeed actually. Well, I failed to direct AI to create this project like by its own, and so I just took over, and I just think it's fun to do myself, and I barely use AI now, but for this project, but yeah, it's really interesting, I think. AI is like super interesting because it has changed a lot of stuff. Like it's totally changed. Like, you know, everywhere, all the tools you use, like AI is everywhere. I mean, I think it's a good thing. But of course, there could be bad things coming out from it as well. But it's like, I don't know. I just from a tool standpoint, I just think it's a nice, really nice tool. Okay, so the call, we have a callee, and the callee we check directly here. Do you use advanced mathematics? I mean, not really. The most advanced mathematics I've been using, well, okay, if you're talking about compiler mathematics, no. The answer is no. I don't use any compiler mathematics at all. Like, I don't try to prove that any program is like well defined or anything like that. The most advanced mathematics I've used is basically in the game that I made or tried to make in the other project. It's like basic, like vector mathematics, very basic physics engine with, you know, velocity, acceleration, and position and all that. Collision detection, quad tree collision optimization. But that's basically it. But nothing in this language is like has math, except for plus, minus, multiplication and division and modular. What's it called? Modulus division, remainder operator. Actually, bit shift. We're gonna have bit shift as well, probably. Okay. Oh yeah, bit operators. I actually didn't add those. I mean, that's very simple to add, but since we have zig backing here, but yeah. What am I doing? So basically, if you call something, when it comes in as a call expression, it could be a function call, but it could also be just an identifier that is like something else. It could be an executable that we're trying to call. So we're checking here if it's a slice. That basically means like we've kind of hard coded in that to mean that we're trying to execute a function. So the slice is actually like the executable name, and then the arguments is the arguments to the executable. So that is the executable call. Now this is just returned directly, so we don't really need to do anything more there. The function call as well, we have if the call is a function ref, we also do that. That should be good. And then otherwise it's just returning the value as is. So I don't think this needs anything more than that. The if expression we already did. Pipeline we haven't done. Do we want to tackle this now? This seems like a huge ordeal, but fine. Look at all this crap here. Yeah. Okay. What are we returning? That's the most important thing. So we're returning this ref down here. I think what we can do is the best way to do this is just move all the refs to the top, perhaps. Unless we have different compilation results. No, we don't have any other returns. So I'm gonna move this to the top. Actually, you know what? Since we have the register, we could reuse the register here. We could just say that, hey, instead of having this ref, we could just return the register directly. Actually, we could change the fork so that it doesn't actually receive a ref. It just sets... It just returns the... Yeah, that makes a lot of sense, actually. Yeah, let's do that. Because we didn't have that before, just because of the reason where we didn't actually have the register. But now we can actually just say location. And we'll do the same thing. Return. Well, this is gonna be, yeah, it's gonna be that one. So fork now actually does not have a result location. It's just gonna return. It's just gonna set. It's gonna be set the result register instead. Yeah, we didn't even format that out, so that's fine. Okay, cool. So we don't have a result. We don't have this. And we return a location. Awesome. Yeah, and we have to now figure all this out. Compile function call. Yeah, so now we don't even need a ref for this. We can simply return. Yeah, we get the handle here, and we return that. Cool. Simplifying. Okay, let's wait with this one because this is way more involved. Here is the initial thing. I think we just ignore these. We don't really need wait for these, so we don't really care about this. And you, of course, do not have a location where you stored. Great. Awesome. It's like having a register simplifies a lot of things. Although you have to be careful about wait, what happened? Source, destination, standard in, yeah. What's the issue? Wait, is it return? It's deleting more than it should. Oh man. Okay. Compile executable call. Sure. Let's see what we can do here. This thread is stored in this ref, but now we don't have that, so we can do like this is the handle, the thread handle. Okay, and then this would be from the thread handle. Actually no, because we're doing it here. No, this is the okay. This is a separate instruction set, right? This is a separate set, and we have another ref that we get from exec. That's right. So the same thing with exec actually. Let's remove ref. This would be, you know, exec handle, and we wait for that. So same thing here. Now this returns a location. Whoops. Awesome. We'll go here, change exec also. We don't have a result. Very good. You don't exist. There we go. And of course we only have one thing there. Very nice. So this is the result register. Okay? And we're doing all this compilation here, but it's a different set of things. So it's not the instructions directly after this fork. So we can still return this thing here. Now we could move this down here so that it's maybe more clear what's happening. Like we're compiling a different set of instructions over here. Now we return to the original instruction set, and we add a fork instruction. We get the register out that we return. What are the differences of Zig with C? How familiar are you with C? So basically both languages are like low-level manual memory managed programming languages. You have pointers. You don't really do pointer arithmetic too much in Zig though, but you could. But it's not really, I guess it's like, you could say that Zig has more safety features. It definitely has more better support for C's preprocessor is replaced, you could say, with Zig's comp time features. Which is kind of a way to kind of creating types, creating how could you say it? Man, why am I having so hard time to think about this? It's basically you can have a bunch of comp time code that runs in comp time instead of runtime. But the comp time also makes it possible to create, struct types based on. It could be based on runtime values. If it's, let's say, it's an enum value, you could switch on the enum, and then have different things happen, based on the enum value. Different. It doesn't sound amazing, but it's the comp time stuff basically replaces all of the preprocessor stuff in C. It's much better. It's I would never. Of course, you could do things with the preprocessor that you can't do with the comp time, because it's just a string replacement algorithm thing. So you could kind of make up syntax and do all weird kind of stuff, but it's also okay, well, do you really want to? Hello, Crimson. Thank you. So how are things progressing? So I think it's progressing pretty good. Currently, I'm implementing, I guess, a better foundation of how to kind of pass values around in the IR language. So we're closing in even more on assembly land with this language here. And I added a a register that is supposed to be used for results. I also added a register for stack frames. So now, hopefully, at the end of this, we will be able to call the same function multiple times without it freaking out. So yeah, that's basically where we're at right now. So that is going to be a huge, this is like a one of the largest undertakings I've done. But basically it's also because of that we already had a bunch of stuff implemented. So it's also a matter of like, okay, how can we adapt the things we already have to this new thing? But it's pretty, I mean, it's just that we have to go through all of these things and adapt them. So it's not that big of a deal, actually. We didn't really need to redo too much stuff. But basically here now, we have this fork instruction. Before, we could choose to store it in like a ref. But now the refs are stack based. So what we're doing like now, I changed the fork to actually just return, well, store its handle, the thread handle, in the return register. So now we get this register out instead that we use. Yeah, it's a lot of like technical things, but it's like that's what this is. It's a bunch of technical things that's happening, and we're trying to figure it out. So, okay, are we done with this now? So let's see. We compile a bunch of. So we compile expressions. So okay, this is also bad. This doesn't really work. Oh no. This is the same issue as we have with the stream or the string literal. We have a loop of that we compile all the expressions, but the problem is that the result value is like could be volatile if it's stored in a register. The result register, to be exact. So actually, we probably want to push this to the stack actually. Yeah. Maybe. The thing is here, we're pushing like the fields, so we're creating kind of like a struct, and we're pushing that as a value onto the stack, and that does not mean that this struct gets converted into a byte array and gets pushed onto the stack as a bunch of bytes. Because the stack is actually not a byte string. The stack here, it's a value dynamic array with a union enum as a value, and one of those values is a struct. But the fields here, they are just, they could be like references to the register, for example. They could be anything. So, this does not work to do it like this. And the way that I did it before was actually a lot easier, because I just pushed all the arguments onto the stack and pushed the number of arguments to the stack, and then the exec, the evaluator, when it saw the exec instruction, it would just pop. First, it popped the number of arguments from the stack, and then it looped through to pop all the rest of the arguments, and then it would execute with those arguments. So that's like way easier than what we're trying to do here. Is like we're trying to push like some weird struct here, but it was like kind of like an experiment as well to get like structs working. But yeah, the stack is kind of weird because it's not a byte string. You don't think of it like a byte string here. It would be a byte string in assembly code, but it's not here. But so if you would have a struct I mean, either you would have just the whole struct in bytes here, or you would have kind of like a pointer to the struct or something like that. But yeah. So yeah. So this needs to be rethunk. Maybe we'll just go back to the. We'll just go back to. Because yes, we're just gonna go back to whatever we had before. Like we're just gonna push all the arguments onto the stack instead. Yeah. So let's see. How do we gonna do this? So we're pushing. First, we're gonna push. We're gonna do like an iterator. This is gonna be a reverse iterator of the arguments. Okay. And then we're gonna loop through that to get an argument. And this is, of course, this is an expression. So what we're gonna do is we're gonna compile that. Call this expression. And we get the result. And then we're gonna push. So push the argument to the stack. Okay, so then, you know, we push all these things. And then at the end, yeah, and that happens in like a reverse order. And then the last argument is going to be executable. We're going to push the executable as well. Well, and then we're going to push, how many arguments do we have? We have the executable plus something, which is going to be the argument's length. So we're going to push this as a integer. And there we go. So that is that's what we're pushing on the stack. And then when the executable, or when the evaluator comes across this exec instruction, we have all these things pushed on the stack. So first it would pop this off, which now we know how many arguments are on the stack. Then we're gonna pop the executable name. And then basically, well, it's gonna loop through and pop all of these and put it in a list. And then we can actually use that list to execute. So that's what we can do there. So now there's no problem in looping through this because we're storing the value on the stack now. But before it could have stored it in like a register, which would then be lost the next time you compile the next thing, which stores it in the same register. But now we actually push it on the stack as well. So now we store it there. So that is good. Okay, is there anything else we need to do? We don't need you. We don't need you. We don't need you. We do need the instruction set. That is fine. And yes. I think also when we add a new instruction set, we need to kind of push a new frame directly here. If you don't have a frame, yeah, we always need like a frame when we do this. So I think actually we need to push the frame as well. So push frame. Oh shit. Push frame. What do you do? I mean, I guess we could do like original instruction set is equal to self current structure set, and current structure set equals to original, and then now let's set this to, well, this is the new instruction set. It's going to be instruction sets items length -1, and we're going to set you to the new instruction set, and then we're going to push the frame. Source is, I mean, I guess now we need a source here. And then yeah, and then here we return new instructions. There we go. Compile, don't have anything there. Also, we don't need to push the frame now because we're doing that already. We don't need to pop the frame either. Like in the end, we would end up with some stack there, but that doesn't matter. Okay, and then you are also null here. So we don't have any source for this. Alright, yeah, so everything else should have a source. Alright. Okay, back to work. I was not satisfied. Executable call. Let's check this again here. So we create a new set. We populate it with a bunch of arguments that we compile. We execute this. Now there might be some issue here, like this compilation here, like the arguments, because the arguments actually come from a different thread. So it's like if we're using like local variables to push in here, or registers. No, that wouldn't work. We could, it could refer to things on the stack or on, yeah, I don't know, whatever. It could be an issue, like because this is get compiled and it's going to be executed by another thread. That thread now has different contexts. So when this is compiled, we pass a bunch of arguments to a function or an executable. Those arguments need to be known by that thread, but it hasn't been an issue so far. Okay, I guess we'll see. It might become an issue when we start to implement bindings and then pass bindings in. We'll see how we'll do things. Okay. So now we push that, we have the execute thing, we wait for that, so that's fine. And then we revert to our original structure set, we do a fork that we then just return. Okay. I'm satisfied now. Let's see, function call, very simple. We just fork to that address and return the thing. Simple. I mean, we don't really do anything with arguments, but that's not implemented yet, so there we go. This should be fine. Already did this. Although we could probably remove this push frame because it should only be used for function calls actually. So we don't really need this frame unless we're in a function call, because function calls are kind of like Yeah, that's where we need a stack frame, right? No, not the function call. It's going to be the function declaration. Yeah. So here we actually need, like, we need to do push frame, and then after we will get, yeah, down here we'll do pop frame, yeah, we're adding a new set, we're changing to that. We have a frame, we have the function body, we check if we need to wait for that, and then we do. Doesn't really work with async, you know, calls, but this is like forcing sync here, but if we get async multiple times, yeah. And then we pop that frame. I mean, the function calls always execute in a different thread anyway, so do we even need frames? Because they're gonna have their own stack, so we don't even need this, I don't think. It's only if we call it like synchronous, like if we don't spawn a thread for that. Yeah. Okay. Okay, and then we have compile block. We have a new ref, we have pipe. Yes. We create a set for the block. This ref, I'm gonna move this up here just so we gather all the ref declarations up here. This ref is like the result ref. So actually I don't think we even need this. So I'm gonna remove that. And then this gets forked. We're gonna get the block result, which is then, oh yeah, that's forked. Okay, yeah. So the set is actually created here so that we can fork into it, and then we actually create the set down here, which does all this crap over here. So, okay. However, we don't actually, we can wait with this fork until we're down here. So there we go. So that we can return that. Okay. And then this thing, we don't need this. We will get the block standard out thread here instead. And then we compile a bunch of statements. Oh, that's right. So we fork here. Wait, now I'm confused. Oh yeah, we fork the standard out stream. That's right, and then we wait for that later. So I think we want to push this actually, because we need to store. We need to store it. This is gonna do all kinds of weird stuff. So we need to store this thing. So we're gonna push that. Push. From. Well, we know that this is kind of like, this is gonna be converted to, yeah, this is gonna be, I think, a common pattern here, where you fork and you want to store it, so you want to push it, but then this is a location and this is a value, which doesn't work with generic locations, but it does work with registers. So this would, but now we kind of know that this is a register. So this would just be the register here. But then you are a register location thing. Well, it could be like init. Yeah. So I feel like that would be a common pattern. We'll see how common it is though, but okay, and then we compile all these things, and then up at the end we need to wait. What do we wait for? Well, we're gonna wait for this thread. So actually we'll do pop. And we get this again, although we already have it up here. I mean, since we kind of know that this is the same thing, I'm just going to do this. So we pop the thread handle and we wait for it. We restore that. We call fork. And yeah. Okay. It's gonna be interesting, all kinds of weird issues we're gonna get when this is all done, because there's a lot of quirks in here. It feels like everything is like different, which is cool. Alright, so where are we now? Compile pipeline, right, the major thing here. So what is going on here? We're creating like a bunch of refs, apparently. Right, each pipe has its own ref, okay. Well, that's fine. The ref is stored on the stack, yes, so this should be a stack location basically. We're piping those, creating pipes in these locations, that's fine. And then, actually this is not fine anymore. And the reason why it's not fine is because it's thread local. But I guess we could see if we can make it. Well, it is thread local until we do fork. This fork here, yeah, and these forks, these things are going to be pushed. So we're kind of transferring from one thread to another. So I think that should be fine. Okay. So what's happening here? We're creating stage sets. Yes, each stage has its own instruction set. We're going through all the stages except the last one. We are creating a stage set instruction. We're populating it here. We're compiling an expression. We get the result. We fork, which is where the issue is. So we'll remove that. Now we could have destroyed the result by forking. So we actually need to kind of push this now. Push the result, fork, and then wait for... Is waitable result? Right, we're forking. Actually, we could fork before. We don't need to wait. We don't need to do that. We fork. Or do we actually? It depends on the pipe. If it's like if it closes before it's like connected or anything, but I don't think it does. These pipes are keep open. Well, at the end we turn off keep open. Here we're turning on keep open, so it shouldn't like be destroyed or anything. If we fork it here and it starts to stream and it's like, oh, we don't have anything, so we're close. We compile the expression to connect everything. I don't know. Let's do it like this. This feels safer here. So let's do like push, and the value is result value, and so we push that, and then we fork, and then after we fork we actually get like this on the stack. So we do like pop, and then you are popped. Right, you are I guess this is two different things. Like if we check first if this is waitable, it's different than if it's not waitable. I think it's gonna be always sort of waitable, I think. Maybe. But yeah, if it's waitable, we cannot do all this. We push that, we pop it, and then we simply wait for it. Yeah, we're waiting for the content of this expression. But then this fork we're not actually waiting for. We're just streaming that. And then at the end we set this to false, so this should exit itself. Okay. But then if the result is not waitable, that kind of means that it's like a comp time known value. So what does that mean here? I think we're just gonna have an error here right now. Unsupported expression or whatever. Yeah. Okay, so we're checking here, is it waitable? If it's waitable, we store the value, we fork, we pop it back, we wait for it. All right. So that is all the stages. Okay. We go back to our original. We now create a fork instruction that we need to remove these things. Okay, so we don't actually care about these forks, so we can just throw away that result. Those are just gonna get created, and then we have the last thing is the only thing we care about. So we have the last set. We compile that expression, check if it's waitable, we wait for that. That's fine. Okay. And then the last, we don't actually need this ref now. Last fork handle. There we go. Right, let's just do this. Okay. That's it in this file. Now we're on to the evaluator. I'm gonna, yeah, the context also is gonna change. What is happening here? No field name data in location. Alright. This is now gonna be like init amps. Alright. No field name adder instruct ref. Okay, yeah. The refs are interesting because this is never gonna be a ref actually. Yeah, the refs are no longer a part of this. It's always gonna be the stack. So this is like an error or something. I'm just gonna do like unreachable here for now. Actually, let's do like panic. So we can find it. Well, we can find it unreachable as well, but whatever. All right. Location. That's right. So to address. If you have a ref, yeah, this doesn't really work. Is this called when we have a ref? I'm just gonna say unreachable here as well, or like an error. Yeah, I'm gonna do like, I'm gonna add this down here. Unless we can supply more context, we can't actually resolve that. Okay. We have some issues with the formatting. Register T for register. Maybe this is in value, not sure. What is this? The value. Register T. Wait. No, this would be F. Actually, yeah. Okay. Access of union field enable struct is active. Well, let's do this so we can see where it comes from. Value 12. Well, that's where it exists. That is the thing. Switch resolve value 633. Wait, switch must handle all possibilities. Okay, we get more issues here. Oh wait, yeah, because there was other things. Is active. So tag enum type deserialize value to 40 register. Oh yeah, right. Can we take a struct? You know what? I'm not sure if we ever gonna have this in here. I think I'm just gonna do unreachable here. Because it's only if we're gonna refer to the register from like the read-only data, which doesn't make sense to me. Okay, now we're on to the virtual machine. So the context, well, the refs are actually, that's not gonna exist anymore. So we can just delete that actually. What is going to exist though? Like what's going to exist are the registers, but that's not shared, that is private. So we're gonna have registers. So let's just add those. Maybe, well actually, we kind of have register already. So let's just add stack. Well, the stack counter we already have. It's gonna be the item link there. The stack for, okay, so we already have all the registers. Well, except for one. So we have the result register. So the result register is going to be, I think, a value. I think it's just going to be a value, actually. All right. Cool. Now we have that. So what do we do now? I think we have to go through like everything in the evaluator to fix this. But okay, so switch on type, location, yes. Get slice, map address. We get a location, back, and we're gonna switch on abs instead. and we get length plus size. Well, actually, page address. I mean, I guess we have to add get length. I'm just gonna ignore this. Like basically support mod, address mod. We're not gonna have this right now. It doesn't make sense right now, so I'm just gonna do that. Okay, we have some more stuff here. This is the kind of the same thing. We're gonna do like .abs. However, now if this is like a ref, for example, do we even get the ref here? No. Wait, now I'm confused. No, because the instructions could have a... Yeah, the instructions can have a location. That's right. So when we have a value, we're never really dealing with a ref. Right. But we could be dealing with a register. And you are just absolute. So basically, we also need a mod now. So let's get the location. It's gonna be this. Switch on apps. Return. If we get register, we're gonna have to switch on that and see. So if it's like, you know, if it's I guess if it's like instruction counter, right? Instruction counter, we return. I mean, we don't really have anything that uses this, but we have to, now we have to return like thread instruction counter. And turn that into a value. Can we even do that? Do we even need to do that? I don't think we actually use this. So I think if it's an instruction counter, I'm just gonna say, I'm just gonna return unsupported. Yeah. And then we have like stack frame. Now this actually is what something we would want to use. So this would be stack frame needs to be thread private stack frame. But also, we need to kind of handle the mod. So it's going to be like lock mod. God damn it. Let's do. I mean, didn't we have two address? Yeah. Yeah. So we already have this thing. Stack start, stack. Register, unsupported. let's do like, let's add another one called like apply mod to some kind of address. Then we don't do this. There we, well actually we return, let's just return there we go. And no errors. And of course, here we can return apply mod to apps instead. Okay. So over here we would do stack frame, so we would do like apply mod to that. However, we just get a U size back, so we need to do like from address. Okay, and then basically same thing for stack counter, except we would look at the stack items. Or actually, could we get like stack counter here? No. Let's just do that. That would be the current stack counter there. I think that's it for the registers. Oh yeah, the ref. Okay, that was the like we wouldn't ever get ref here because we don't. Yeah, this doesn't return ref anymore. So ref is actually, that should be like unreachable here. Oops. Switch must handle. Oh, what? What are we missing? Oh yeah, results. Oh yeah, but result is a value, so we could just return thread private result in register. There we go. Okay. Yes. So now we have like, we have some. Okay, let's do this one first. Switch must handle all possibilities. So what are we missing? Could we what are we missing here? Register, materialize string for a register. It's a reference to something. I'm just gonna put it over here in the pile of non-things. No field name, result, instruct. Okay, so before we tackle this, I'm gonna be away 1 second here. All right, Penny. Okay, now. So the exec instruction was changed. Now, what's happening here is that what happened? I'm not sure what's going on with this. With the maybe it's something weird with the, like the electricity or something. Like the keyboard keeps stopping. It stopped again. What the hell? Okay. Okay, now it seems to work. Okay. No, it stopped again. What the? Do I have like too many devices going on here? I have no idea. What the hell? Hello, hello. I accidentally removed my network cable, so great, not great. Let's see if it works now. It should be working, yeah. Okay. Yeah, my cable, my keyboard is like disconnecting and stuff. So when I tried to like fix it, I accidentally unplugged my network cable. All right. It's nice that we're back so quick here though. Okay, no field, yeah. So let's see now. Yeah, so before we actually need to do this here. So we don't have this thing here, actually. So we do that, and we take this back now. So basically, and also this will be thread now, thread private stack pop. Yeah. So now we keep all the arguments on the stack instead. So we pop the first one is the number of arguments in argv. And then we do this, which is going to be thread private now. Thread private is pop. And we don't do this. Okay, we create the argv thing. Never mind this part here. We loop through and pop all of the arguments in order, in reverse order. It's like it has to be reversed since it's on the stack. And that is that thing. Well, we're not doing it in reverse order here. We were doing it in reverse order when we pushed it. So the first thing we pop is the executable name, and the second is the first argument, and so on. Yeah, and then everything else should be the same except for the result. That's right. So we do all this. Argv value. So this one should be. Yeah, so this is, so we'll do this and we'll say argv length plus 2. So there we go. And down here, since now we don't have a result anymore. So what we're doing, what we should do is we should store the result in the thread result register now instead. So we should always have that. I'm gonna do this for now, and we're gonna do these things, except we're gonna do thread private result register is equal to that. Yeah, so that's a pointer. So we would set the thing to that. Okay. And then continue. So that's good. Okay. Now, there is a slight difference here as well. It's like before, we wouldn't add this closable if we didn't need to store it in a location. But now we kind of always implicitly store the location in the result register, which is different now because now we always add these closables. But I don't think that should be much of an issue. It's just that we're kind of saving them here, and yeah, that should be fine. Where it's just that it's stored there. But it's a little bit less, I guess, less efficient. I don't know. Okay, so that should be it for that. Now the other thing that changed was the fork as well. We should get an issue there, by the way. Why is this unused? What? Oh, because it's like the only thing we're doing is sync. Okay. Which is probably gonna be removed. Okay, we should get an issue at fork as well. No member named address in here. Okay. So this is where you create a new ref. That's right, this needs to change as well, because here we need to push now instead. So we don't actually do this or this. This we might want to do, but what we do is we do push, which is doing this part. So we just push here. And what do we push? Well, this is just a name. Wait, is it really just... No, it's not just a name. It's supposed to be a ref. Yeah. Okay. So we push... Wait, it's not actually supposed to... No. Yeah. Actually, yeah, it is supposed to just be a name. But we don't really do anything with the name here. It's just to be able to show it in the instructions, just for debugging purposes. But really, what we're doing here is we just push something on the stack. Actually, we just push a void. Yeah. That's what we're doing with that. Switch on type location. Okay. Set a ref. So we don't actually... Do we set a ref? Yeah, we do, because this is now an actual location. So this could be a ref, actually. But now we don't really have refs get pointer. What we have is the stack. So this would be more like stack. Do we have anything here for stack? No. Well, let's do this. Let's go in here and we'll say get ref pointer. And this would be like, I don't know, value maybe. Whoops. Right, and then this would be like private stack items. And then it's gonna be the current stack frame actually. Plus, no, yes, plus and then of course we do need the ref itself. Is it instruction ref? No, it's location ref. Where is this thing? Oh, it's its own thing. Okay. Okay, so we have the ref. Now we'll do stack frame plus that. Yep. So stack frame should point to basically itself, I think, or no. It should point to the thing after itself, I think. And then the stack address is gonna point to the thing there. Yeah. Hopefully this works. We'll see. I think I have to go through this mental gymnastics again to understand if this actually is gonna work or not. Okay. Yeah, especially with the if statements and loops and everything. Okay, so let's go back now to where we were here. So let's do like, instead of this, I'm gonna say it's gonna be thread ref pointer, and then this is a value, so I'm gonna say equals this. Well, okay, we could just do this. We can also, I mean, we could have a convenience function like set ref or something. Set ref value. Ref. Okay. Oh yeah, so we have, oh yeah, we have register as well. And then we switch on that. And technically now we can we can change, like, well, I wouldn't really know how to, like, you can't actually change instruction counter though. So I'm gonna say this should be like some kind of error. And then we have stack frame. That would be thread private stack frame is equal to value. Now this has to be an integer, so we're just gonna take that. And then I mean, I guess it could be something else. I guess it could be, well, it has to be resolved though. It has to be a resolved value. So I'm gonna say it's probably gonna be a U integer. And then we're gonna have the stack counter as well. This is also like, but the stack counter, like if you, let's say we set the stack counter, setting the stack counter is weird because it's like because we are working with an array list. I guess we have to kind of do this. So basically this is going to be like thread private stack. Is there like a resize? New size is going to be this integer. Adjust list length to new length. Additional elements contain value undefined. Invalidates pointers if all memory is needed. Yeah. So yeah. So I guess we could do that. All right. Fine. Switch must handle all possibilities. Oh yeah. And then we also have this one, which I constantly forget about. Now this is the result register, so we just set it to the value itself, and that's all we need to do there. Oh. Wait. Found void. Ah, I see. Right. So well, everything here is gonna continue, so okay, let's just do this. And then return continue afterwards. There we go. Error unions ignored. Okay. Pipe instruction pipe, no field name ref invocation. Right. Right, the pipe instruction actually has a result. Oh. How often do we do this? Not super many times. And it's okay. I was tempted at first to kind of say, okay, well, should we do the same thing here? I guess we could. What is the issue we need to solve here to make this work though? Because what I was thinking, like, okay, we could do the same thing with the pipes, so we could remove the result thing and then implicitly set the result register instead. But that would require a lot of changes as well, and I need to kind of make this work here now. No field named ref. Right, this is like abs. So refs get points. So actually we just say, let's just say like set ref, and the ref it's just gonna be, I'm just gonna say ref abs here, or actually like abs ref. And then the value is pipe handle. Now the problem that we need to look out for also though is that when we use the pipe here, we have to make sure that this ref doesn't like disappear. Also, we're pushing these refs onto the stack now, so we have to pop them at some point. Are we doing anything with these refs? Yeah, we're doing stuff over here. You're a ref. Yeah. Oh yeah, because these are like pipes. Okay. So I think like after here, okay. I guess after here. You know what? Let's just push a frame here. Because if we push a frame, we... no. Yeah. I'm gonna check this out here. You're gonna set the stack counter to the value of the previous... Like... It's a location, so we're looking up what is the value of this stack counter -1 in the stack. That's what we're trying to say here. Like, this is gonna happen when we resolve the value. It's gonna look into the register, but also it's different as well because we could refer to the actual value of the stack counter, but I don't think we ever gonna do that actually, except for here, actually. Or wait, no. Yeah, see, this is an issue here. Like here, we're trying to say that hey, we should set stack frame to be no. We are restored. This should be the content of the stack, yeah. And then the stack counter is pop. We're kind of popping it here. But at the same time, we're not. Because, yeah. Yeah, this is looking into the content here. This is an issue. Okay. I mean, in assembly code, you have like different modes. So you would have one mode that would look in the contents of the register, and then another mode, or in this like the stack, and then another mode that would, you know, look at the actual value of the counter itself. Which this is not the idea. The idea here is to look in the content, I think. Maybe we can add a thing here. We just need to be able to like represent it somehow. I'm just trying to figure out what a good way would be. I mean, we could have a separate value type, I guess. This would be like register, the actual register value, or then we can have register, I don't know. No, but that would be like a lookup though. That would be like an address lookup. We don't really have a way to kind of modify an address. Or taking like, for example, like a register and dereferencing that, or like an integer dereferencing that. That would be... So, okay, so maybe what we do want to have is like a dereference. And then this would be either a uinteger well, let's just say an address or a register. And if you dereference, what would the mod do? Would it change the address after it's resolved from the register? Yeah, I guess it would. Or wait, no. It wouldn't. Well, yes, it would, actually. Well, okay, no. You wouldn't resolve, you wouldn't dereference first and then modify because you don't know what's in there. You would modify the address and then dereference, yeah. Dereference. Man, there's so many tools and stuff you need for this to work. Compiler, okay. So what's this gonna be? This is gonna be, so let's see, the stack frame is gonna be set to the content, which means we need to dereference. Is that the correct term, dereference? Like, yeah, the idea is that we look at the content of the address. And then this one would actually be the actual like counter value -1. So it would be equivalent to popping, basically. But what I wanted to do is actually not set this to be that. What I wanted to do is actually what I wanted this to be was that we want to actually not the reference here. I wanted to set this to the register of SF. No, we do want to dereference. Yeah, because the thing that I want to have here is basically, even if let's say we have a stack frame and then we pushed a bunch of stuff, but if we pop the stack frame, we could always pop it and go back to. We don't have to pop every item that we've pushed. The idea is that we would pop the frame only, so then that is like a very simple instruction. So basically, we're looking at the current stack frame register, because that points to where in the stack we started here. So if we want to go back to the previous frame, we would just pop. Yeah, we would subtract 1 from that to get back to the previous one. And then actually this is now set to the stack frame, set to the previous stack frame -1, which, or the current stack frame -1, which is going to be where we push the previous stack frame value. So that should be correct here. However, now we need to swap these instructions because we don't want to. No, wait, this is not gonna work because this is gonna be an error. God damn it. Okay, maybe we can temporarily store. It wouldn't be an error if we were working with assembly, but now we're working with zig, and when we do this, or when we do this rather, it's gonna resize the array, the stack array. So it's like it's gonna fail if we do this after. So we have to kind of store this in a result first. Oops. So let's store in the result register, which does mean that now we actually changed that, so we should temporarily no, we have to temporarily. No, this doesn't work. Oh my god. Okay, so we changed the stack frame where it should be. Yeah, we set it to the previous value, and we also pop, except we don't want to pop to the, we don't want to change the result register. So we're using this pop thing for that. But the issue is that now we've lost the value. I mean, we could introduce another register, but it's I mean, couldn't we could push, yeah, we could push the, we could just push the stack frame first, so we save that. We save the stack frame. We then set the stack frame to be the previous one, because we want to use this stack frame to be able to pop back up. And here we're gonna do, yeah, so now we don't need to pop this. We can simply say, okay, well, let's set. Actually, we can use dereference again. So the current stack counter -1 would refer to this now. And it means that we are setting the stack counter to be the previous stack for, yeah, it has to be like popped again as well. God damn it, so we need another. But now we can use, now we simply, we do this, which basically is like taking taking like setting the register to the itself -1. Yeah. Okay. All right, cool guy. So we save the stack frame, the current one, so that we can pop back quickly to it. We restore the stack frame to the previous stack frame. We set the stack counter to be the content of the stack counter -1, which should refer to this thing here, which was the current stack frame. So we go back up to the start of the stack frame. But we also need to subtract another one, because then we will be restored fully here. So there we go, I think. I hope. Okay. What's happening over here? Will you complete it by February? I have no idea. Maybe. No, probably not. I mean, it's just 2 weeks left. I wouldn't put that kind of deadline. I don't really have a deadline. Man, time flies. All right, switch my this. So you will be. What's happening here? The call. What's going on? Oh yeah, we added the reference. That's right. Okay. Pop frame register. Oh yeah, edit apps. That's right. Okay. Pop frame. Yeah. There's also. Yeah, now we're getting here. Okay. We're gonna get so many bugs later, like when this is done. This won't. Yeah, this doesn't happen. We could do it. Actually, we don't do it at all. Did I remove the correct thing? Actually, pop frame. No wait, that's scopes pop frame. That's different. Okay. Okay, that was lucky. No field name result. So you ate noodles? What? No? God damn it, why do I get like 1 million notifications right now? Okay. What? Okay. That sounds like, you know, you should go to another train. No field name, this, that. Okay. Okay, what's that? Oh yeah. So now we're back. Okay. I got lost there for a second. Fork results. So yeah, so now we should, same thing with the with the executable. We will now say no, it's not a ref. It's thread private result is equal to that. And we do push these things. That is correct. Yeah. Actually, that is actually interesting because every thread already has 3 things on the stack. So when we create a new ref, we shouldn't use, well, where is that instruction set? So when we create a new instruction set, we actually kind of always have those 3 things. Well, at least in the name of a fork. Yeah, the fork destination. So actually, when we do this, we should modify. Let's set the instruction set to be the destination set. We're gonna have the original set, and we wanna set that to back to the original. But while in here, we also push. No, we already pushed a wait. Yeah, we already have a frame, but we should say like current frame and then add 3 to that, because that's what we're doing with the fork. It's adding 3 things to the stack, so we should do that here as well. So now the thread counter or the stack counter should be correct. Hopefully that's still the thing. Code guy, yeah, you don't need to worry about that. Oh, that's weird, man. Maybe, I don't know. And is it that illegal? No field name ref instruct location. Oh yeah, these things. Yeah. So the arithmetics and everything else here has a result. That's right. And we're kind of always assuming that it's a ref. I mean, I guess. I mean, really what we should have is like a set location or something. Thread results location is going to be what? Results. Thread is a thread context. Where is that? And then location is that. And then the value is that. And I guess we can switch on the location perhaps and check if it's a ref. We are going to say thread set ref to the value. Let's just do that for now and we'll figure it out. Yeah, try. Okay, same thing here. Try set location. Location is log expression results. Value is result. Okay, the value is this, I guess. Yeah. And then here, try set location. Thread location is result. Value is result. People from older generation, okay. I would think the other way around, but yeah, I don't know. Okay, okay, we don't have compiler errors, so that means everything should work now. Let's start with the basics. How much do you want to bet that this is gonna work? First try. You're wrong. No, you probably guessed that it wouldn't work. Unsupported address type. Okay, interesting. Let's see what we get from here. Unsupported address type. Where do we get that? Here. Okay. So let's add some more context here. Or actually, let's go to, where is this even called? It's called over here. To address. So we have a bunch of places. We have, let's see, start with a compiler. Add slice. Okay. Location, add data. You're supposed, that's read only, so that's fine. Push location. I don't think this is even used. I'm just gonna remove this. Yeah. Resolve location. Now this could be something maybe. Pipe handle, yeah, these are definitely threads, or I mean refs now. And then it's gonna go into the location to address, and then we're not gonna be able to do it anymore because refs are not supported like this. So yeah. Okay, resolve location we need to fix here. I think we had like resolve value, right? Resolve value did. Well, actually, no, it's unreachable. Okay. let's do this. If it's a ref, that's set. Oh, so we never had like get. Okay, I guess that's what we're doing here. Get ref pointer yeah. And then like inline else or else it's gonna be this. Okay. Is that better? No? Still same error. Do we actually build? Yes, we do. Okay. No, but it might be. Yeah. The register. Actually, register. Yeah. So the register. So now this should refer to the actual like value of the register. So we're gonna switch on the register type. And we're gonna say if it's like instruction counter, we should, that's like an error. Resolve value error. And then if it's a, well, actually, you know what? Shouldn't this just be resolve value? No. Okay. This is very spaghetti, but okay. Well, let's just do this. So if it's a stack frame, we will do well, it's just going to be a U integer, and the thing is going to be thread private stack frame. Counter is going to be the same thing, U integer, thread private stack items length, and what else? Results. And that's just going to be private results register. Okay. However, in the case of these things, we actually do have the mod to take into account. So we can do like apply mod to these things. Of course, it doesn't have to be an address like it states in the variable name here, but there we go. Whoops. Okay. So that's the register. Then we have the reference. dir And the dir. Why is that unknown? Oh, that's not a val. That's not a location, right? Wait. But then this shouldn't be the absolute. This shouldn't be the value. That this should refer to the. Yeah, this should refer to the thing. Like, we should never be able to get the register from here, actually. It should just be this. I'm just gonna copy that. I'm gonna do that. And then we'll go back to if it's something else, actually, yeah, register. We'll do that. I'll just add ref there as well. What's this? Location. There we go. Same thing, except we create a stack address here, I think. Yeah. All right. Okay. What the hell? Still same issue, or well. Okay, let's see. Can we start the debugger? No. So it's like the compilation that fails, I think. So it might be like we're calling to address over here somewhere. From location, are we calling this function? Result from location? Yes, we are on everything basically that we need to return. Oh. Okay, yeah. So actually here we need to do like a switch on abs. And if it's like a ref, we need to do something. No, that doesn't work. We're never getting a ref here. No, we're getting a register. That's not. Right. Yeah, so if we get a register, that means it's a location. Does that mean a dereference then? I think so. Maybe. Well, or you're I think registered. Okay. Now we get something else. Unsupported streaming. Is that... Okay, so we do get the compilation going. So that's good. Okay, and as you can see here, now the read-only data is way less because we're using like instructions to push the data instead of storing like an executable call context in the read-only data. Push stack frame. Right. Set one, push stack frame, yeah. Cool, cool. Yeah. Over here. Push things. Push one. Yeah, that makes sense. Exec. Wait for the results. Cool. Now where's the issue? Stream S0. Unsupported streaming. S0 is a stack thing. Okay. Interesting. So let's go to the evaluator and the stream thing. Okay, so we get unsupported streaming. It would be nice to see what it actually is. So, but let's see here. So this all is supposed to work then. Stream is a location. I mean, if this is a location, what we want to do is we want to resolve the location, right? Still, okay. Yeah, still same error. I'm gonna see if we compiled. Yes. All right. So let's log out. Streamy. Register, okay. Okay, let's go to the compiler. Let's go compile initial, because that's where this is happening. So here's the stream thing, and we're talking about thread standard in, which is just a stack location, and that stack location has things in it. That actually should happen here somewhere. Here. So we're creating some pipes and we are adding them to the stack. Now these pipes, I mean, that's just, yeah, that's a value. How do we get a register? I don't understand. That shouldn't happen. I don't think. So let's go in here. Now the stream here, the location should be the stack. So it's supposed to be doing this part down here. Stack 0, so it should be get like the first item on the stack. To address, that's gonna be like the stack, yeah, this thing here. Apply mod shouldn't really do anything because we don't have that for this one. And then from address is just initializing that. Resolve value checks. Okay, we're mapping the address. Yeah. So it's like if it's more than stack start, we do this. That should all work. And then if it's stack, we're gonna grab the item on the stack. I think what we'll do is we'll add a command to the debugger that is called the stack, which will just list whatever is on the stack. Stack print stack. And let's see, French. And we'll print, we'll go through private stack items. And let's get the index as well. And we'll do try print. And then at the end, do that. There we go. And actually, we also return continue as well. Okay. Now, we're gonna do parse command, and we'll just add stack. All right, cool. Now we got the stack command. We can go into here and we can say stack, and we don't have any stack, which makes sense because we haven't done anything yet. So let's look at the instructions. All right, let's step, and after this we should have things on the stack. Whoops, did I see? Okay. Now we're all here at stack. Although this stack is... No, this does have things. Okay, so we have a stack frame. Oh, the stack... Oh, okay. Okay. The stack numbers are now... Before, you can see here we're hard coding these. But now it's like every set, the first thing refers to the stack frame, which kind of doesn't make a lot of sense though. Well, it makes sense if it's not in its own thread, but the sets are basically always in their own sets. if we step now, where are we? Over here. We get 2 frames. What the hell? Right. So you can see that this is wrong. Okay, I think simply what we need to do is just bump those numbers up by 1. So thread standard in, no, that's over here. So you will be 1, 2, and 3. Yeah, they should be stored somewhere. Are we actually standard? Yeah. See? No, wait. No, that should be fine. Thread handle. Okay. Okay, we still get the issue though. So, well, if we look at the stack now, well, we still get like, we have like pipe ID 0, 1, 2. If we look at pipes, well, we don't really see, but if we look at the instructions, now you can see that this is S1, S2, S3. So we're now referring to the correct pipes here. All right, instructions. Stream S1. Okay, so now we actually did get through there. And we're forking. Okay, here we go. Was that stream S3? You know what we'll do? We'll go to stack, and I will print out. I will actually go through all the threads. Thread. Okay. Fork. Now you can see we have 2 threads. First thread stack is here, second thread stack is here. And oh, wait. Now this is wrong. All of a sudden. These threads have it the other way around. Okay. What the hell? That's actually weird. see, we are pushing the frame. That's the first thing that happens when we create an instruction set. That should be the only instruction. So what is happening there? We push that. That's the stack. Now we have those on the stack. We fork this. Oh, I see. This is the... Wait. Oh, this is the first instruction that actually gets executed. And then it goes into the set to execute the push. I see. Okay, well, in that case, we can just do... we can just do this. We can go back on this. And then we can go to compile initial. Actually, wait, where is that push frame actually? Push, where's this coming from? It's coming from this, the first instruction set. Oh, I see. Okay. I mean, maybe I should have just put the standard IO stuff in like the private thread context instead of having them on the stack. But then that requires a whole new type of location. So, but now we do have registers though, so we could put it into like some kind of register type thing, I guess. But yeah, the solution here is, I mean, there's several ways to fix it, but basically when we first, because we need an instruction set first, but we don't want to, and we need a frame. But we kind of want the forward instruction. Yeah, we kind of wanted this to be the first instructions. We don't want... Okay, whatever. Let's just make a special thing here. I even had the helpful informational comment there about this specific issue that I actually ran into. And I'm gonna say initial instruction set, and we don't push the frame, we don't do this, and we do this, but we can just return here. Or we could say add initial, add instruction set, no push frame. now you do no push frame. What the hell? Why can't I remove this? There's something weird with 3-seater and the null. It's super weird. No, you don't. No, you do have that. Yeah, yeah. But no push frame. There we go. But then in initial, we would do it after forward IO. Now we do push frame. Okay, so this is gonna put them on the stack, the pipes. This is going to also, this is gonna put the thing on the stack. So that should be good now, hopefully. Okay, now we get another error. So now you see forward standard IO is first. Now we get the pipes on the stack. Now this is how it looks. Okay, good. Where is the error happening? Oh, we actually do get things happening. Wait, why did you exit? What the hell? Okay, the main thread exited. That's not great. And then we wait for the register unsupported. Okay, okay. Well, let's look at that first. Evaluator wait. Okay. So same thing here. I think we should do like location instead. Is that enough? Okay, now we're stuck. Actually, let's look instructions. Yeah. See, we're just forking and then exiting. So there's something missing here. Did I just remove the wait instruction? But it should work anyway, I think. Push and then execute. And then we're waiting for that. Wait, where's the streaming? The pipe that should stream. They're streaming, yeah. And then it's streaming. You exit. Okay, so when the main thread exits, the streams end. So that shouldn't actually happen. But we don't. That's how we do it right now. So I'm thinking what we should do is we're gonna say yeah, we need to look at what's happening here because there's something missing in, I think, executable call maybe, or statement, compile statement perhaps. I think, yeah, we're missing like the waiting thing. In the main thread, so compile statement. And then we're checking like is waitable, you know, the result, and then we're waiting for it. The result here is going to be, I think, yeah, the executable call actually. So it's a call, and it's an executable call. And in the end, we return, this should be the register. Yeah. Oops. So that should be the register that we return as a location here, and return that. And that gets returned over here. And the statement should look at that to see, hey, are you waitable? It should be a register. Oh, hang on. Okay. Maybe it's because of this conversion here. No, fork. Where are you? Yeah, see. Where's this? No, this is. Where's compile executable? Yeah. Fork inherit. Okay, yeah. Fork inherit. So we do from location. What do? You're saying from location on the value, on the location, and if it's a, oh, it's a dereference. I'm gonna do null for address now. Yeah, let's just do this. It's gonna be some kind of issue in the runtime now. Or not. What the hell? What? I got it working again. What the hell? I really didn't think this is gonna work now. What the f... Okay. Yo piano. Thank you. Okay. You're waiting. That's great. Execute, wait. Awesome. Okay. I was expecting a lot more trouble here, but okay. Let's see if this works. The pipeline. No. Access of unified user and dereference is active. Interesting. So where did you get? You got down to set register. I see. Ah, I see. Okay, I see. I think I know what's going on. So it's gonna be set I think it's here. Also, why does it take so long? Yeah, 367. Yeah, it's here. So set this to something. What is this something? We need to kind of resolve this value, I think. And that's what I was thinking that we should do, but I didn't do it. Or whatever, let's do it now. So we resolve the value, and then in the end I'm expecting to get a U integer, perhaps. But also, are you counting? No, that's just result. Okay. What if it says register? Okay, so we need to add register here then. Now we need this part. But we don't have. Oh, yeah. Okay, you are. Oh shoot. Well, okay. Let's do that. If we have it, we will return apply on you. And I'll add you to register as well. Okay. Oops. Yeah. So apply mod. There we go. Okay, now if we have dereference, I'm gonna do resolve location. where the location is a register. No, it's init. I'm just gonna do this. I'm just gonna hard code in that. And the mod is that. Right, your apps. There we go. Do you have the wrong error type? Oh man. Will this work? No. Yeah. That doesn't work. Okay. Location error. Member function expected to I see. I need to wrap this there. Oh, but then we have location mod as well. So this would be like location, no, set location, yeah, set location, apply mod. There we go. Just that. No. Wait, I mean this. There we go. And you do not do much there. You just set the value. Okay. Nope. Same place, integer overflow. Oh. Interesting. Stack frame, -1. So we're pushing the stack frame. And we're setting stack frame to be the stack frame -1. Where's that coming from? Yeah, it's this one. So we're pushing the stack frame. We're setting stack frame to be actually the dereference of the previous stack frame. No. Yeah, well, the previous stack frame, yeah. Okay. We have two, I think, yeah, two places where this is happening. It's here and here. Compile if no else. We have a frame and the pipeline where we don't actually have a stack frame. Okay. So let's just remove that. That might be the issue. Perhaps. Why is it so slow? Oh, now it might be stuck actually. Okay. Okay, that's waiting on a pipeline. We're pushing some results. What is that result? Hang on. Okay, I can see an issue here. We pushed the register here. You see the issue? We should push what's in the register, not the register. It's like the kind of reference to the register. So push. Yeah, we should never push like the reference to the register. That doesn't make sense in no way, shape or form. So when we push we get like a value, but this value is going to be resolved first. Yeah, I think I really need to look over how the dereferencing, the addressing is working, because it's like right now it's a total mess. Like we are assuming things here and there. There's like no clear, consistent way of talking about, you know, what is the non-dereferenced value? Are we talking about the non-dereferenced value, or are we talking about, like, are we talking about the address, or are we talking about the dereference value? Like, what are we talking about? Like that, there's no clear, consistent way of dealing with that. So that, yeah. But I'm going to say resolve value, I think. So that needs to be like looked over and fixed, but yeah. Okay. Hopefully that doesn't mess other things up though. Because if this is like an address, we don't really push addresses, I don't think. But now it's gonna reach into the value of the address instead. If it's a register, it reaches into the actual register. If it's a dereference, it reaches into the location of that. So it's always, we always get the value out. But resolve location does dereference. Yeah, I think. Okay, well. No. Whoops. Hang on. There we go. So push SF. What is that now? 0. Now that does make sense. However, I think it's wrong as well. But well, it should be 1, I think. Maybe. Well, I mean, it depends. Yeah, but now we get like, we don't get the reference to the stack frame. We get the actual value, which is correct. Push, push, push. Now wait for R. Great. We pushed. Now we're pushing R. Or did we push R already? Yeah. Look at this now. This is now pushed onto the stack, which is like a thread handle. So it's a thread that refers to number 6. So that is now correct. So we're saving the value that was in R instead now. Good. And here we're pushing something else. So what do we get there? We get like a slice. And that's fine as well. 6 is waiting. Okay. Okay. Nothing's happening really. We're executing cat. All right, standard in is open. Waiting. Okay, we're preparing to execute the next thing, which is grep, I think. I mean, we always see stand above now because of the wrap thing. Wait, cat into hello, what the hell? This is gonna block anyway. Okay, so it might not be an issue. Okay, I'm gonna okay. Let's do grep. Oh my god, it just works now. What the hell? That shouldn't happen. What was this? Grep. Yeah, it just works now. What the? Okay, I'm gonna assume this doesn't work. Okay, it doesn't work. Good. Because I was like, this is black magic right now going on. What is this? Blocks. Yeah. I mean, it doesn't crash and burn though, but it's it also doesn't work. So it might have something to do with the pipes. The inner pipes might not get streamed or something. Okay, but we have done a lot of good things now. So we added a this is going to be it for this time, but I'm just going to go through like what we've done. So basically we added a way to talk about, yeah, we added stack frames. So basically a way to kind of call functions multiple times. Actually, that we could test that as well. Does this work? Oh, this actually blocks. That's not good. Yeah, there's probably something weird going on with the pipes. Yeah, I'm gonna guess. Yeah. But if we only call you, will that work? No. Okay. Yeah, there's definitely going on something weird with the pipes. But the whole point here was that we could call this multiple times without crashing and burning, and that works now. Hopefully, it's gonna work later when we actually fix this. But yeah, so that was the whole point of this, like being able to, and also I think loops would also be basically so that anywhere you would jump to in the program, we would be able to say that, okay, we can rerun this part of the code. Now, of course, if you just jump willy-nilly, you're gonna get like the stack is not gonna be in sync and stuff. But we control how the stack is pushed and popped, and as long as we see that everything looks good, it's good. Okay, anyway, so yeah, so we added like register for results, so now we implicitly set when we fork and we execute that register, so we can use that instead of using a ref, which doesn't work for returning. So we have a way to return a value from some kind of expression or a function call. And that required a lot of remapping. Also, I realized that we should fix the address dereferencing somehow, so we have a clear way of defining that. What else? Yeah, basically retrofitted basically everything to work with the registers now. And well, we have some bugs left, so I'm gonna add this bug here, which is basically well, that is, yeah, so pipe look into the pipe instruction to see why some of the examples are not outputting anything. Okay, so we'll end it there, but we've done some major progress now, and the future is bright. All right, yeah, have a nice day, and I'll see you later.